Imagine waking up one day to a world that feels both deeply familiar and utterly strange. A reality where the solid ground beneath your feet and the steady forward march of time are revealed to be just the tip of a cosmic iceberg. What if everything you see, every choice you make, and every fleeting moment you experience are not isolated events, but fragments of a much grander, more intricate, and largely unseen structure? This is the world we are about to explore together, a universe not confined to the familiar three dimensions of our senses, but one that stretches into realms that defy our intuition and challenge our imagination. At first glance, our lives seem straightforward enough. We exist in a space defined by three coordinates. We can move left and right, up and down, forward and backward. And we are carried along by a fourth dimension, the relentless current of time, which pushes us ever onward from the past, through the present, and into an unknown future. But as science has delved deeper into the nature of reality, it has uncovered a set of rules that seem to border on magic, a subatomic realm where the common sense of our macroscopic world dissolves into a shimmering sea of probability and potential. This is the world of quantum physics, a world where particles can be in many places at once, where the very act of observation seems to shape the reality being observed, and where the linear flow of time itself may be nothing more than a stubborn illusion. To begin this journey, let us start with the simplest of concepts, a single, dimensionless point. It has no length, no width, no depth. It is a pure, abstract location. Now, connect two such points, and you have a line. The first dimension, a world of pure length. Add a second direction, perpendicular to the first, and you create a plane, a two-dimensional world of length and width, like the surface of a sheet of paper. This is the world of geometry, of squares, circles, and triangles. And if you take this two-dimensional plane and fold it, pulling it up into a third direction, you create the three-dimensional space that we call home, a world of solid objects with length, width, and height. This progression seems intuitive enough, but what happens if we continue this pattern? What lies beyond the familiar three dimensions of our physical world? This is where our journey into the strange and beautiful landscape of modern theoretical physics truly begins. The first step beyond our spatial reality is into the fourth dimension, a concept that is most commonly, and perhaps most intuitively, understood as time. In this picture, time is not just a fleeting, intangible flow, but a dimension akin to space. Our entire existence, from the moment of our birth to the moment of our death, can be visualized as a single, four-dimensional object, a world line or a space-time worm snaking its way through the unified fabric of space-time. Your past, your present, and your future all exist simultaneously in this block universe, and your consciousness is simply a spotlight, a point of awareness, moving along this pre-existing four-dimensional reality. But what if this single, linear timeline is not the only one? What if every choice we make, every random, quantum event in the universe, causes reality to split, to branch off into a new, parallel timeline? This is the gateway to the fifth dimension. The fifth dimension is not a new direction in space, but a new direction in the landscape of possibility. It is the dimension that contains all the alternate histories, all the what-ifs, all the different paths that our universe could have taken, branching out from every moment of choice. There is a timeline where you took that job, and a timeline where you did not. A timeline where the dinosaurs never went extinct, and a timeline where they evolved into intelligent, sentient beings. The fifth dimension is the space of these branching possibilities, a vast, ever-growing tree of alternate realities. As we ascend further up this dimensional ladder, the concepts become increasingly abstract, moving from the realm of physics into a space that feels closer to metaphysics. The sixth dimension allows us to not just conceive of these branching timelines, but to fold the space of possibilities itself. It is a dimension that would allow for a kind of shortcut between different, seemingly distant branches of the multiverse. It is the plane that contains all the possible histories that could have arisen from the same initial conditions of our Big Bang. A complete, phase space of our specific kind of universe. The seventh dimension marks an even more profound leap. It is the dimension that contains the set of all possible universes that could have started with different initial conditions. This is the realm of universes with different physical laws, different fundamental constants, different numbers of spatial dimensions. It is a library of all possible cosmic beginnings, each one giving rise to its own unique, six-dimensional tree of possibilities. The eighth dimension is the plane that contains all of these different cosmic libraries, allowing for a comparison, a branching between these fundamentally different kinds of realities. The ninth dimension takes this to its logical extreme. It is the dimension that contains all possible physical laws, all possible initial conditions, all possible histories, all at once. It is the ultimate ensemble, the set of all possible universes. And finally, we arrive at the 10th dimension, in the conceptual framework of string theory, the leading candidate for a unified theory of everything. The universe has 10 spatial dimensions and one of time. The extra 6 dimensions beyond our familiar 3 are thought to be compactified, curled up into a tiny, complex geometrical shape at every point in our space. But in a more conceptual, hierarchical sense, the 10th dimension can be thought of as the ultimate point of origin, a dimensionless point of pure potential from which all the lower dimensions, all the possibilities, all the universes emerge. It is the everythingness that contains all possible realities, a concept so vast, so all-encompassing, that it transcends our ability to visualize or even fully comprehend. This journey through the dimensions is not just a mathematical game. It is a profound and humbling exploration of the potential richness and complexity of reality. It suggests that the universe we experience, with its familiar 3 dimensions and its steady forward-moving time, may be just a single, thin slice of a much grander, multidimensional, and endlessly fascinating cosmic structure. A structure whose deepest secrets are hidden in the unseen, and perhaps unknowable. Dimensions that lie just beyond the horizon of our perception. The strange and counterintuitive world of quantum mechanics provides another, equally profound, challenge to our classical common-sense understanding of reality. At the subatomic level, the very fabric of existence seems to be woven from threads of uncertainty, of probability, and of a deep participatory relationship between the observer and the observed. The solid, definite world of our everyday experience dissolves into a shimmering, ghostly sea of potential. The fundamental constituents of our universe, the particles that make up every atom in our bodies, are not solid, billiard ball-like entities. They exist as waves of probability, their properties not fixed and definite, but existing in a superposition of all possible states at once, until the moment of measurement. And it is this act of measurement, of observation, that seems to be the magical ingredient that collapses this wave of potential into a single, definite reality. This raises one of the most profound and unsettling questions in all of science. Are we, in some sense, creating reality by the very act of observing it? If a particle does not have a definite position until we look at it, then what does it mean to say that it exists before our observation? This is a question that has divided physicists for a century, leading to a host of different and often bizarre interpretations of the quantum world. Some physicists take a pragmatic view, arguing that these quantum effects, while real and measurable in the subatomic realm, are confined to that realm, a process known as decoherence, The constant interaction of a quantum system with its environment is thought to rapidly destroy the delicate superposition of macroscopic objects, ensuring that the classical world of our everyday experience remains stable and predictable. The quantum possibilities are still there, but they have faded into the background, their interference effects washed out by the noise of the environment, leaving us with a single, coherent, classical reality. But others have been drawn to more radical conclusions. The many worlds interpretation, for example, proposes that the wave function never truly collapses. Instead, every quantum measurement causes the entire universe to split into multiple, parallel branches, with each branch corresponding to one of the possible outcomes. In this view, we are not collapsing reality. Our observation is simply entangling us with one particular branch of a vast, ever-growing multiverse. We are not creating a single reality. We are choosing our path through an infinite, pre-existing tapestry of all possible realities. This is like tuning a radio. All the other stations are still broadcasting, but we are only experiencing the one we have locked onto. This line of thought leads to even deeper and more perplexing questions. If observation is the key to actualizing reality, then who or what was the first observer? What existed before the emergence of life, of consciousness, in the universe? Did the cosmos exist for billions of years as an uncollapsed, ghostly sea of pure potential, waiting for a conscious mind to come along and give it form? Or was there some other, more fundamental form of observation at play? A cosmic observer that has been collapsing the wave function since the very beginning. The relationship between observation and the flow of time is another area of deep mystery and speculation. We experience time as a relentless one-way arrow, moving from a fixed past to an open future. But what if this arrow of time is not a fundamental property of the universe, but an illusion, a story that our consciousness constructs? What if, at a deeper, multidimensional level, all of time past, present, and future exists simultaneously? In this block universe picture, the act of observation at a single point in time, the present moment, could be what creates the appearance of a consistent historical past leading up to that moment. It is a radical idea, the notion that our present awareness could, in a sense, retroactively create the billions of years of cosmic history that we observe. It is as if, from the ultimate vantage point of the 10th dimension, a single choice, a single act of observation, collapses not just a present state, but an entire, consistent, four-dimensional space-time history. This is a concept that strains the limits of our language and our logic, but it is one that is being seriously explored at the frontiers of theoretical physics. The very terms we use, observer, measurement, consciousness, are laden with philosophical baggage. For some, the role of the observer is synonymous with the role of a creator, or even of God. The idea that a divine cosmic mind is constantly observing and therefore creating. The universe is a powerful and enduring one that is found in many of the world's spiritual traditions. From a scientific perspective, this is not a testable hypothesis. But the parallels between these ancient metaphysical ideas and the strange, participatory reality suggested by quantum mechanics are undeniably fascinating. They suggest that we may be on the verge of a new synthesis, a new understanding of reality that can bridge the long-standing gap between the inner world of subjective experience and the outer world of objective science. What is clear is that the simple, mechanistic picture of a universe that exists out there, independent of our own minds, is no longer tenable. We are not separate from the reality we observe. We are deeply and mysteriously intertwined with it. The act of attention, of awareness, is not a passive process. It is a creative, world-shaping force. And the question of how far this power extends, of what other hidden layers of reality might be accessible to a new and more refined form of consciousness, is perhaps the most exciting and profound adventure that humanity has ever embarked upon. The familiar intuitive experience of time as a steady, unidirectional flow, a relentless arrow pointing from the past, through the present, and into the future, is one of the most fundamental, and yet most mysterious, aspects of our reality. The British astrophysicist Sir Arthur Eddington, in 1928, coined the evocative phrase, the arrow of time, to capture this powerful one-way nature of our temporal experience. We see glasses break, but we never see them spontaneously reassemble. We remember yesterday, but we have no direct knowledge of tomorrow. This seems so obvious, so deeply woven into the fabric of our existence, that we rarely stop to question it. And yet, when we look at the most fundamental laws of physics, this arrow of time is strangely absent. The equations of Newtonian mechanics, of Maxwell's electromagnetism, and even of Einstein's theory of relativity, are all time reversal symmetric. They work just as well for a process running forwards in time as for one running backwards. The laws themselves do not distinguish between the past and the future. So, if the fundamental laws are symmetric, where does the manifest asymmetry of our world come from? Why do we experience time as a one-way street? The standard answer lies in the second law of thermodynamics, which states that the total entropy or disorder of a closed system always increases over time. The universe began in a state of incredibly low entropy, a highly ordered and uniform state, and it has been evolving towards a state of higher entropy ever since. This provides a thermodynamic arrow of time, a statistical directionality that explains why systems in our universe tend to move from order to disorder. But this just pushes the question back a step. Why was the early universe in such a special, low entropy state to begin with? This is one of the deepest unsolved problems in all of cosmology. But what if there is another, even more profound, layer to this mystery? What if the arrow of time is not just a property of the universe, but is intimately linked to the nature of life and consciousness itself? Consider a simple chemical reaction, where two molecules, A and B, combine to form a new molecule, C. We perceive this as a forward-moving process, but the underlying physical laws would allow, in principle, for the reverse reaction, for C to spontaneously break apart into A and B. In our observed reality, however, the forward reaction is overwhelmingly dominant. Why, some have speculated that the very emergence of life, the self-organizing processes that arose from the primordial soup billions of years ago, may have somehow selected a preferred direction of time. Perhaps the complex information processing systems that we call life can only maintain their delicate, low-entropy state by surfing the universal wave of increasing entropy. Life, in this view, is a process that creates local pockets of order by exporting disorder to its environment, a process that is fundamentally tied to the thermodynamic arrow of time. But this leads to a fascinating and deeply speculative thought experiment. If the emergence of life is somehow linked to the arrow of time, could there be other forms of life in other corners of the cosmos, or perhaps even in a parallel universe, that have evolved in a universe with a reversed arrow of time? What would such a reverse time life form be like? To us, its actions would appear to be a bizarre reversal of causality. Its effects would precede its causes. A shattered cup would reassemble in its hands, and then it would place the whole cup on the table. It would be born old and die young. Communication with such a being would be a logical impossibility, a dizzying paradox of crossed causalities. The science fiction trope of a backward-flowing timeline provides a powerful way to explore these conceptual puzzles. Imagine an alien civilization whose history unfolds in reverse relative to our own. Their arrival on Earth in our year 3000 would be, from their perspective, the beginning of their historical interaction with us, their subsequent conquest of the planet, which from our perspective would look like a slow, inexplicable retreat, would be, for them, a story of glorious expansion. Who, in this paradoxical encounter, is the victor? The question itself dissolves into meaninglessness. The very framework of a shared, linear narrative breaks down. While this is a highly speculative scenario, it is one that is not entirely disconnected from the frontiers of theoretical physics. The idea of a mirror universe, a universe where the laws of physics are a mirror image of our own, including a reversed arrow of time, has been seriously proposed as a potential solution to some of the puzzles of cosmology, such as the nature of dark matter. In this picture, our universe and this mirror universe could have been born together in the Big Bang, moving in opposite directions in time from a common origin. The ultimate nature of time may be even stranger than these scenarios suggest. The block universe view, which arises from Einstein's theory of relativity, suggests that all of time past, present, and future exists simultaneously as a single, four-dimensional space-time manifold. In this view, the flow of time is an illusion, a product of our consciousness moving through this pre-existing static block. If this is the case, then the arrow of time is not a property of the universe itself, but a property of our perception. Perhaps our brains are wired in such a way that we can only process information sequentially, creating the subjective experience of a flowing now that moves from a remembered past to an anticipated future. But what if this is just one possible mode of consciousness? Could there be other forms of awareness that could perceive the block universe in a different way, that could access the past and the future with the same ease that we access different locations in space? And what if, at an even deeper, multidimensional level, the very concept of a single timeline, whether forward or backward, is an oversimplification? In the higher dimensional reality suggested by some theories, our entire four-dimensional spacetime could be just one slice of a much larger, more complex structure, a structure that contains all possible timelines, all possible histories, all at once. From this ultimate atemporal perspective, the distinction between forward and backward, between cause and effect, might cease to have any meaning. It would be like looking at a complex, woven tapestry. From the perspective of a single thread, there is a clear, linear path. But from the perspective of the whole, there is only the intricate, beautiful, and timeless pattern of the weave itself, the arrow of time, which feels so fundamental and unshakable to us, may be just a local, emergent, and perhaps even illusory feature of our particular corner of a much grander and much stranger cosmic reality. Imagine a reality where every decision you have ever made, every path you have ever taken, and every possibility you have ever considered all exist simultaneously, woven into the vast, multi-dimensional fabric of existence. This is a universe where the simple, binary logic of yes or no, of this or that, becomes the fundamental building block of an infinitely complex and beautiful cosmic structure. This binary viewpoint is not a formal scientific theory, but a powerful conceptual framework, a lens through which we can begin to grasp the mind-bending implications of modern physics, from the quantum world to the highest, most abstract dimensions of reality. It is a way of seeing the universe not as a collection of things, but as a cascade of choices, a story written in the simple yet profound language of binary decisions. At its heart, this viewpoint suggests that the universe, in its most fundamental state, is a realm of pure, unmanifest potential. The Big Bang, the moment we perceive as the beginning of our cosmos, can be reimagined not as a random, chaotic explosion, but as the first great binary toggle. The first yes in an infinite sea of no. It is the moment when the universe chose existence over non-existence, something over nothing. This single, primordial choice unleashed a cascade of subsequent bifurcations, a torrent of binary decisions that have shaped the evolution of our reality ever since. The theory of cosmic inflation, with its period of hyper-accelerated expansion in the first fraction of a second, aligns beautifully with this picture. It can be seen as the rapid, exponential unfolding of the possibilities contained within that first binary moment, the unfurling of the cosmic blueprint that was encoded in that initial choice. From this ultimate, atemporal perspective, the very concept of a before the Big Bang is transformed. It is not a question of what existed in a preceding time, but of what existed in a state of uncollapsed, pre-binary potential. It is a journey backward not in time, but into a realm of pure, undifferentiated indeterminacy. A shimmering fog of possibility waiting for the first creative act of distinction. The first yes or no, to give it form. This binary, decision-based framework is not just a feature of the cosmos. It is a fundamental feature of our scientific inquiry itself. The history of science is a history of branching paths, of competing interpretations of the same data. Isaac Newton's laws of motion and gravity provided a powerful and precise framework that reigned for centuries. But when Albert Einstein introduced his theory of general relativity, which described gravity not as a force, but as the curvature of a dynamic spacetime, he did not render Newton's laws wrong. He offered a new, deeper and more comprehensive interpretation of the same phenomena. Newton's theory became a collapsed state, a highly accurate approximation that works perfectly well in the low-gravity, low-velocity regime of our everyday experience. Einstein's theory represents a different branch of the possibility space, a different way of looking at the same cosmic rhythm. The two theories are not mutually exclusive in a simple, binary sense. They are two different and complementary layers of a single, multi-layered truth. We see the same pattern in the development of our understanding of matter. The classical picture of solid, point-like particles gave way to the quantum picture of wave-particle duality. And string theory, in its most ambitious form, seeks to unify these different pictures by proposing that the fundamental constituents of reality are neither particles nor waves, but tiny, vibrating strings of energy. Each of these theoretical shifts is not a negation of what came before, but an expansion of the possibility space, a new and more nuanced way of interpreting the fundamental, binary choices that seem to govern the cosmos. This leads us to a profound and unsettling question about our own place in this branching. Decision-based reality. If every quantum event, every choice, creates a new timeline, a new branch of the multiverse, then where are we? The many worlds interpretation of quantum mechanics suggests that we are on all the branches at once, that there are an infinite number of us, each living out a different reality. But our subjective experience is one of a single, continuous, and coherent life. Why do we perceive only this one, particular path through the infinite, binary forest of possibilities? The answer may lie in the nature of consciousness itself. Perhaps our consciousness, our point of awareness, is the very thing that navigates this multidimensional landscape, collapsing the wave function of our own experience into a single, linear narrative. We are the thread that is being woven through the tapestry, and the path we take is the story of our lives. This brings us to the ultimate paradox, the tension between free will and determinism. If all possible outcomes exist somewhere in the multiverse, then what is the meaning of our choices? The binary viewpoint offers a fascinating, if speculative, resolution. It suggests that while all paths may exist in a state of potential, our consciousness, through the act of choice, is what makes a particular path real for us. The universe, in this picture, is deterministic in that all possibilities are governed by the underlying mathematical laws of the wave function. But we experience free will because our consciousness is the agent that chooses which of these deterministic paths to actualize, to experience as our reality. We are both the characters in a pre-written play, and the audience that, by its very attention, brings a particular performance to life. This idea finds a powerful fictional expression in the works of authors like Philip K. Dick and Jorge Luis Borges, who constantly explore the nature of reality, of alternate histories, and of the power of the mind to shape its own experience. It is a vision of the universe that is both deeply mechanistic and profoundly magical. A universe where the rigid laws of physics and the creative freedom of consciousness are two sides of the same, fundamental, binary coin. The binary viewpoint is not a scientific theory in the traditional sense. It is a conceptual tool, a way of thinking, a new lens through which to view the mysteries of the cosmos. It invites us to see the universe not as a static, predetermined machine, but as a dynamic, interactive, and endlessly creative process, a process of constant becoming, a story that is being written, moment by moment, choice by choice, in the simple, yet infinitely profound, language of yes and no. And as we stand at the crossroads of our own lives, facing the infinite, branching possibilities of our own future, we can take some comfort in the idea that we are not just making a choice in the universe, but that our very choice is an act of creation, an act that helps to shape the very fabric of reality itself. At the heart of our existence lies a paradox that is both deeply personal and profoundly cosmic. The universe we inhabit appears to be exquisitely and improbably fine-tuned for the existence of life. From the strength of the force of gravity to the precise mass of the proton, the fundamental constants of nature seem to have been set to just the right values to allow for the formation of stable atoms, of long-lived stars, of planets with complex chemistry, and ultimately of conscious, questioning beings like ourselves. If any of these values were even slightly different, the universe would be a sterile and barren place. This apparent fine-tuning has led to a great deal of debate among scientists and philosophers. For some, it is the most compelling evidence we have for the existence of a divine creator, a guiding hand that has purposefully designed the cosmos with us in mind. But for many cosmologists, there is a more natural, if no less astonishing, explanation, the anthropic principle. In its simplest form, the anthropic principle is a statement of selection bias. It says that the reason we observe a universe that is hospitable to life is because we could not, by definition, observe one that was not. We are here to ask the question precisely because our universe is one of the rare, life-friendly ones. This principle gains its full explanatory power when it is combined with the idea of a multiverse. If there are countless, perhaps an infinite number of other universes, each with its own randomly assigned set of physical laws and constants, then it is no longer a surprise that at least one of them, by sheer chance, would have the right conditions for life. We are simply the winners of a cosmic lottery of unimaginable proportions. It is a powerful and elegant explanation, but it is one that relies on the existence of a vast and perhaps forever unobservable ensemble of other realities. The anthropic principle, in this context, becomes a kind of statistical inevitability. But it also raises a host of new and perplexing questions. If every possible outcome of every quantum event is realized in a separate branch of the multiverse, as the many worlds interpretation suggests, then what is the status of these other realities? Are they as real as our own? And why do we experience only this one single, coherent timeline. The complexity of our own existence provides a powerful, if metaphorical, parallel to this cosmic puzzle. The human eye, for example, is a marvel of biological engineering, an instrument of such intricate and perfectly coordinated complexity that it can seem, at first glance, to be the product of intelligent design. How could such a thing have evolved through a series of random, unguided mutations? The answer, of course, is the power of natural selection acting over immense geological timescales. But the anthropic principle offers a different kind of explanation, a different way of looking at the same improbability. It suggests that in the vast, multidimensional possibility space of all possible biological forms, the existence of a complex, image-forming eye is not improbable at all. It is a necessary condition for the emergence of an observer who can look up at the stars and wonder about the nature of reality. The eye and the universe it observes are part of a self-consistent, participatory loop. This brings us back to the binary viewpoint, the idea that reality is a cascade of choices. The Big Bang itself can be seen as the first great binary toggle, the choice of existence over non-existence. The subsequent period of cosmic inflation was the rapid unfolding of the possibilities contained within that initial choice. And every subsequent event, from the formation of the first atom to the evolution of the first living cell, can be seen as a further collapse of the universal wave function, a further selection of one path from an infinite, branching tree of possibilities. Our universe, with its specific set of laws and its capacity for life, is the result of a particular and very long sequence of yes-no decisions. The anthropic principle, in this light, is not just a statement about our universe. It is a statement about the nature of observation itself. Our consciousness, our ability to observe and to ask questions, is what collapses the vast, superpositional reality of the multiverse into the single, experienced reality of our timeline. We are not just living in a universe that is fine-tuned for us, we are, in a very real sense, the tuners. This is a radical and deeply challenging idea, one that places consciousness at the very center of the cosmic story. It suggests that the line between the subjective and the objective, between the mind and the world, is not as clear as we once thought. But what about the other timelines? The other universes where the cosmic dice roll came up differently? What about the universe where the laws of physics are slightly different, where JFK's assassination was thwarted, where a different sperm fertilized the egg that became you in the many worlds picture? These realities are all equally real, branching off from our own at every moment of choice. They are the might-have-beens that are somewhere else, the what-is. We can never access them. We can never know them directly. But the anthropic principle, combined with the multiverse, suggests that they are an integral part of the grand cosmic tapestry. Our reality is just one thread in this infinite weave. This is a vision that can be both humbling and liberating. It is humbling because it removes our own personal story from the center of creation. But it is also liberating because it opens up an infinite space for possibility, for creativity, for the endless, beautiful, and sometimes tragic unfolding of all that could ever be. And as we stand on the precipice of our own choices, we can do so with a new and profound sense of the weight and the wonder of our own creative participation in the grand and perhaps infinite drama of the cosmos. The concept of time travel, long a staple of science fiction, becomes a far more complex and philosophically charged endeavor when viewed through the lens of a multidimensional, branching reality. The classic paradoxes of time travel, like the famous grandfather paradox, are all predicated on the assumption of a single, linear, and mutable timeline. If you travel back in time and prevent your own grandfather from meeting your grandmother, you create a logical contradiction if you were never born. then you could not have traveled back in time to do the deed in the first place. But in a universe governed by the principles of quantum mechanics and higher dimensions, the story is not so simple. The many worlds interpretation of quantum mechanics offers a clean, if mind-bending, solution to these paradoxes. When you travel back in time and alter a past event, you are not changing your own history. You are simply creating a new branch of the multiverse, a new parallel timeline. In this new timeline, you were indeed never born. But in your original timeline, the one you departed from, your journey into the past is simply a part of its history, and your absence is its future. You have not erased yourself. You have simply moved to a different branch of reality, becoming a kind of time orphan, forever disconnected from your own origins. The popular film Back to the Future plays with a hybrid of these ideas. Marty McFly's meddling in his parents' past causes him to start fading from existence, a visual metaphor for the paradoxes of a single timeline model. But the eventual outcome, a new and improved present, suggests a kind of timeline editing that is more in line with a branching reality. Another proposed solution to the paradoxes is the Novikov self-consistency principle, which posits that the universe is fundamentally paradox-proof. Any action a time traveler takes in the past was always a part of that past's history. You cannot change the past because your actions were already factored into the timeline that led to your own existence. You are not an editor of history, but a character in a script that has already been written. The film 12 Monkeys is a brilliant and tragic exploration of this idea. The protagonist's journey into the past is not an attempt to change it, but a futile and predetermined loop, where his actions are the very cause of the events he is trying to prevent. He is a ghost in his own history, unable to alter the inevitable unfolding of a fixed, four-dimensional block universe. These different models of time travel, the branching multiverse, the self-consistent loop, are all attempts to grapple with the deep, logical puzzles of causality in a universe where the past might be accessible. But the introduction of higher dimensions adds another layer of complexity and possibility. If our four-dimensional space-time is just a brain floating in a higher dimensional bulk, as some theories suggest, then time travel might not involve moving backwards along our own timeline at all. It might involve taking a shortcut through the bulk, a wormhole that connects two distant points in our own space-time. This is the classic science fiction trope of a hyperspace jump, and it is an idea that has a tentative, if highly speculative, grounding in the mathematics of general relativity and string theory. But what about the 10th dimension, the conceptual point of origin that contains all possible realities, all possible timelines, all at once from this ultimate atemporal vantage point? The very concept of traveling through time loses its meaning. Past, present, and future are not a sequence to be traversed, but a single, unified, and timeless landscape. A time traveler, in this context, would not be a being moving from one moment to another, but a form of consciousness that could shift its point of awareness from one part of the block universe to another, experiencing different moments, different timelines, different realities, with the same ease that we shift our gaze from one object to another in a room. This is a level of reality that is far beyond our current comprehension, but it is a logical extension of the ideas we have been exploring. The binary viewpoint, with its cascade of yes/no decisions, provides a useful way to visualize this. Our experienced reality is one particular path through this infinite binary decision tree. A time traveler who changes the past is simply forcing a different branch to be taken at a particular node, creating a new, alternate history. But from the perspective of the entire tree, all branches coexist. Nothing is ever truly lost or changed. It is just a matter of which path is being followed, which story is being told. The paradoxes of time travel. then are not necessarily logical contradictions that make it impossible. They are conceptual challenges that force us to expand our understanding of the nature of time, of reality, and of causality itself. They are a sign that our intuitive, linear, and single timeline view of the world is a profound oversimplification. The true nature of reality may be a far richer, more complex, and more wonderfully paradoxical tapestry of interwoven possibilities, a tapestry where every choice matters and every path is, in some deep and mysterious sense, real. The quest to unify the fundamental forces of nature, to find a single, elegant theory that can describe all the phenomena of the cosmos, is the holy grail of modern physics, and the key to this quest may lie in the existence of unseen, higher dimensions. The story begins in 1919 with a remarkable letter sent to Albert Einstein by a little-known German mathematician named Theodor Kaluza. Kaluza had made a startling and beautiful discovery. He had found that if he took Einstein's equations of general relativity, which describe gravity as the curvature of a four-dimensional space-time, and reformulated them in 5 dimensions, something magical happened. The equations naturally split into 2 parts. One part was the original, four-dimensional theory of gravity. The other part was, to everyone's astonishment, Maxwell's equations of electromagnetism. It seemed that the electromagnetic force, the force responsible for light, for electricity, for chemistry, was nothing more than the curvature of a hidden 5th dimension. This was a breathtakingly elegant and powerful idea. It suggested that the two seemingly disparate forces of gravity and electromagnetism were just different aspects of a single, unified 5-dimensional geometry. Einstein was initially captivated by the idea, and he helped Kaluza to get his paper published, but the theory had a problem. Where is this 5th dimension? We do not perceive it in our everyday lives. In the 1920s, the Swedish physicist Oskar Klein proposed a solution. He suggested that the 5th dimension is compactified, curled up into a tiny, microscopic circle at every point in our space, a circle so small that it is completely invisible to us. This Kaluza-Klein theory was a beautiful and revolutionary idea, the first serious attempt at a unified field theory, but it ultimately failed to be a complete theory of nature. It could not account for the other 2 known forces, the strong and weak nuclear forces, and it made some incorrect predictions about the properties of particles like the electron. But the core idea, that the fundamental forces of nature could be a manifestation of the geometry of hidden, extra dimensions, was a powerful one that would lie dormant for decades, only to be resurrected in the 1980s with the rise of string theory. String theory, in its modern form, requires the existence of not just 1, but 6 or 7 extra spatial dimensions to be mathematically consistent. And in this framework, the Kaluza-Klein idea is reborn in a much richer and more complex form. The different forces and particles we see in our universe are all determined by the intricate, multidimensional geometry of these curled-up Calabi-Yau spaces. This idea of a multi-dimensional reality is not just an elegant mathematical curiosity. It offers a potential, and deeply profound, explanation for some of the greatest mysteries of modern cosmology, the existence of dark matter and dark energy. Together, these 2 enigmatic entities make up 96% of the total energy density of our universe. The ordinary baryonic matter that makes up the stars, the planets, and ourselves is a mere 4%, a cosmic afterthought. We are living in a universe that is dominated by substances whose nature we do not understand. Dark matter is the invisible gravitational scaffolding of the cosmos. We see its effects in the rotation of galaxies and in the gravitational lensing of light, but we have never been able to detect the dark matter particle directly. Dark energy is the mysterious, repulsive force that is causing the expansion of the universe to accelerate. Its origin is a complete enigma. The idea of extra dimensions provides a new and tantalizing framework for thinking about these mysteries. In some brain world scenarios, the particles and forces of the standard model are confined to our three-dimensional brain, while gravity is free to propagate in the higher dimensional bulk. In this picture, dark matter might not be a new type of particle at all. It could be the gravitational influence of matter on a nearby parallel brain, a shadow universe separated from our own by a tiny distance in a fourth spatial dimension. We cannot see the matter on that other brain, but we can feel its gravity, leaking across the dimensions and creating the effects we attribute to dark matter. This is a speculative, but testable, idea. If dark matter is indeed a gravitational shadow from another dimension, it could lead to subtle but detectable deviations from standard general relativity on small scales, which could be searched for in high-precision laboratory experiments. Dark energy, too, could find a home in this multidimensional picture. It could be a manifestation of the energy of the bulk space itself, or a result of a force between our brain and other parallel brains. The accelerating expansion of our universe could be caused by the gravitational repulsion from a nearby massive brain in the extra dimensions. This would be a profound shift in our cosmological worldview. The destiny of our universe would not be determined by the matter and energy within it, but by its relationship with a larger, unseen, multidimensional reality. The concept of higher dimensions is one of the most exciting and mind-bending frontiers of modern physics. It is a frontier that is still largely theoretical, but it is one that holds the promise of a deeper, more unified, and more elegant understanding of the cosmos. It suggests that the reality we perceive is just a slice, a shadow, of a much richer and more complex multidimensional structure. And the great mysteries of dark matter and dark energy may not be mysteries about new substances in our universe, but clues that are pointing us towards the existence of new dimensions beyond our universe. The quest to find these hidden dimensions, whether through particle accelerators, gravitational wave detectors, or subtle cosmological observations, is one of the great adventures of 21st century science. An adventure that could one day reveal the true multidimensional glory of our cosmic home. The concept of control, the idea that we are the masters of our own destiny, is one of the most cherished and perhaps most illusory of all human beliefs. We strive for it. We celebrate it. We build our societies and our psychologies around it. And yet, when we look closely at our own lives, and at the world around us, we are constantly confronted with the limits of our own agency. The story of the person who, through sheer willpower, decides not to get sick, only to collapse with the flu the moment they take a vacation, is a familiar one. The anecdote of the cancer patient who visualizes their immune system attacking a tumor and experiences a miraculous remission is a powerful testament to the mind-body connection. But it is also a rare and exceptional event that is far from a controllable, reproducible technique. The 1993 Washington, D.C. meditation experiment, where a large group of meditators seemingly reduced the city's violent crime rate through focused, collective intention, is a fascinating and provocative data point. But it is also a study that has been heavily criticized for its statistical methodology and its lack of adequate controls. These examples hint at a reality where our consciousness can have a subtle but real influence on the physical world. But they also highlight the profound difficulty of isolating, understanding, and harnessing this influence in a predictable and controllable way. The universe, it seems, is not a simple, linear system that responds directly to our individual will. It is a vast, complex, and interconnected web of influences, A system where our own personal intentions are just one small thread in an immense and intricate tapestry. The framework of higher dimensions provides a powerful and beautiful way to visualize this complex interplay between individual agency and the larger collective reality. In the five-dimensional model of branching timelines, every choice we make, every action we take, creates a new path through the possibility space. Our free will is real, in that we are the ones who are choosing which path to follow. But we are not choosing in a vacuum. Our choices are constantly being influenced, constrained, and shaped by the choices of every other conscious and even non-conscious entity in the universe. We are part of a vast, consensual reality, a shared timeline that is the result of a constant, dynamic negotiation between trillions of different wills and intentions. Imagine your life as a single line, oscillating up and down on a graph. The horizontal axis is time, and the vertical axis is your state of being, your happiness, your health, your success. You may desire to keep your line consistently high, to live a life of constant triumph and joy. But your line is not an independent entity. It is entangled with the lines of everyone around you, your family, your friends, your community, your society. Their choices, their desires, their vibrations are constantly influencing your own. The physicist Christian Huygens in the 17th century discovered the phenomenon of entrainment, the tendency of coupled oscillators to synchronize their rhythms. He observed that two pendulum clocks mounted on the same wall would, over time, begin to swing in perfect synchrony. Our consciousness may behave in a similar way. We are constantly being entrained by the vibrational fields of the people and the culture around us. We are part of a collective, consensual dream. Psychoactive substances can create the temporary illusion of breaking free from this consensual reality, of charting a new, ecstatic path high above the baseline. But this is often a false freedom. The crash that follows can leave us even more deeply enmeshed in the negative, downward pull of our own and the collective shadow. True freedom is not about escaping the system, but about becoming a more conscious and intentional participant within it. It is about learning to navigate the complex currents of the collective field with wisdom, with compassion, and with a clear sense of our own unique purpose. It is about understanding that while we cannot control the entire ocean, we can learn to become skillful sailors of our own small vessel. This brings us to the deep and often difficult question of personal accountability. In a universe of such vast complexity and interconnectedness, it can be easy to feel like a victim of external forces, to blame our circumstances on bad luck, on an unjust society, or on the ill intentions of others. And there is no doubt that these external factors are real and powerful. But the dimensional viewpoint also reminds us that at every moment, we are making choices, we are collapsing possibilities, we are co-creating our own reality. To take responsibility for our lives is not to deny the existence of external constraints, but to focus on our own unique sphere of influence, to become more conscious of the choices we are making, the stories we are telling ourselves, and the vibrational energy we are putting out into the world. It is to recognize that even a single, small, and conscious choice can send ripples of change throughout the entire interconnected system. But even as we embrace our own creative power, we must also embrace our limitations. Our human consciousness, as extraordinary as it is still just one finite perspective within an infinite, multidimensional reality. The higher dimensions of existence, the realms of other universes, of other physical laws, of realities that are beyond our current capacity to even imagine, these will likely always remain beyond our direct control or even our comprehension. We are both powerful creators and humble participants, masters of our own small corner of the cosmos, and children in a much grander and ultimately mysterious universal home. The illusion of control, then is a double-edged sword. To believe that we have no control is to succumb to a state of helpless victimhood. To believe that we have total control is to fall into the trap of arrogant delusion. The path of wisdom lies in the middle, in the graceful dance between agency and surrender, between shaping our reality and being shaped by it. It is the recognition that we are both the artists and the clay, the dreamers and the dream, the individual notes and the grand cosmic symphony. And it is in the holding of this beautiful, paradoxical, and life-giving tension that we can find our true power, our true freedom, and our true place in the vast, interconnected, and endlessly creative unfolding of the cosmos. The 10th dimension. In the conceptual hierarchy we have been exploring, represents the ultimate, all-encompassing reality, the point of origin and the final container for all of existence. It is a concept that is so vast, so total, that it pushes our language and our imagination to their absolute limits. It is the realm where all possibilities, all timelines, all universes, all physical laws are not just potential, but are, in some deep and mysterious sense, actual. To visualize this, let us return to our analogy of the dimensional camera. A first-dimensional camera would just capture a single point. A second-dimensional camera could capture a line. A third-dimensional camera, like our own, captures a flat, two-dimensional image of a three-dimensional world. A fourth-dimensional camera would capture an entire world line, the complete history of an object from its birth to its death, all at once. A fifth-dimensional camera would capture the entire branching tree of all possible histories for a particular object. A sixth-dimensional camera could capture the entire phase space of all possible histories of our entire universe, given its specific initial conditions and physical laws. A seventh, eighth, and ninth-dimensional camera would capture the vast cosmic library of all possible universes, with all their different laws and initial conditions. The 10th-dimensional camera, then, would be the ultimate, final snapshot. It would be a single, dimensionless point that contains, within it, all of these other dimensions, all of these other possibilities, all at once. It is the point of infinite density, not of matter, but of information. It is the everythingness from which the somethingness of our experienced reality emerges. This is a concept that has deep resonances with the ideas of many of the world's mystical and philosophical traditions. The Brahman of the Vedanta, the Ein Sof of the Kabbalah, the Tao of Taoism, these are all attempts to name the unnameable, to describe the ultimate, undifferentiated, and all-encompassing ground of being from which all manifest reality arises. The 10th dimension, in this conceptual sense, is not a place we can travel to. It is the source we have come from. And it is a source that is, in principle, beyond our ability to fully comprehend. The Austrian logician Kurt Gödel, in his famous incompleteness theorems, showed that any formal mathematical system that is complex enough to contain basic arithmetic will always contain true statements that cannot be proven. Within that system, to prove them, you need to step outside the system and use a larger, more comprehensive set of axioms. But this new, larger system will have its own new set of unprovable truths, and so on. In an infinite regress, Gödel's theorems are a profound statement about the inherent limitations of formal systems. And if our universe is, as some have suggested, a mathematical structure, then Gödel's theorems imply that it can never contain a complete and consistent description of itself. There will always be aspects of reality that are true but are unprovable from within the system. The 10th dimension, in this light, can be seen as the ultimate, Metasystem, the all-encompassing reality that contains all the other limited systems, but which cannot itself be fully described or understood from within any of them. It is the ultimate context, the final, undrawable frame of the cosmic picture. The theory of superstrings provides a more physical, if no less abstract, picture of this ultimate reality. In this theory, all the particles and forces of our universe are the result of the different vibrational modes of tiny, one-dimensional strings. And these strings are thought to be vibrating in a 10-dimensional space-time. The specific way in which the extra 6 dimensions are curled up, the geometry of the Calabi-Yau manifold, is what determines the specific spectrum of vibrations, and therefore, the specific set of physical laws and particles of our particular universe. The 10th dimension, in this picture, is the fundamental, underlying reality in which the cosmic symphony of the strings is played. The different universes of the multiverse correspond to different possible geometries, different possible symphonies. Our universe is just one particular piece of music, one particular solution to the fundamental equations of string theory. The concept of the 10th dimension also sheds a new light on the seemingly intractable paradoxes of our own experience, like the paradox of Zeno, which argues that motion is impossible because to get from point A to point B, you must first cross half the distance, and then half of the remaining distance, and so on, in an infinite series of steps. In a classical, continuous space-time, this is a real logical puzzle. But in a universe where space and time may be quantized at the Planck scale, where there is a smallest possible unit of distance and a smallest possible unit of time, the paradox dissolves. The infinite regress is halted by the fundamental, discrete nature of reality itself. In a similar way, the 10th dimension, as the ultimate foundational reality, can be seen as the ultimate quantifier, the point that halts the infinite regress of why questions. Why are the laws of physics the way they are? Because they are the result of the specific geometry of the extra dimensions. Why this geometry? Because it is one of the many possible solutions to the equations of string theory. Why string theory? Why 10 dimensions? At some point, the chain of explanation must end, not in an arbitrary fact, but in a final, all-encompassing, and self-consistent structure. The 10th dimension, in this conceptual framework, is that final structure. It is the ultimate, it is what it is. This is not a dismissal of the question, but a recognition of the limits of explanation. It is an invitation to a state of profound, intellectual and spiritual awe, a state of learned ignorance in the face of a reality whose ultimate nature is so vast, so complete, and so all-encompassing that it can only be pointed to, hinted at, and wondered about. It is the silent, dimensionless, and infinitely pregnant point from which all the beauty, all the complexity, and all the wonder of our multi-dimensional cosmos is born. The intricate tapestry of reality, as woven by the threads of quantum mechanics and higher dimensions, is a reality of profound interconnectedness. The different dimensions are not separate, isolated realms. They are layers of a single, unified structure, constantly interacting and influencing each other. And our own experience, our own consciousness, is not a separate, detached entity. It is a point of intersection, a place where these different layers of reality meet, overlap, and create the rich, multifaceted world we inhabit. To understand this, let us consider the interplay between what we can call physical systems and mimic systems. A physical system is the world of our three-dimensional bodies, of matter and energy, of the deterministic cause and effect laws of classical physics. A mimic system, a term coined by the biologist Richard Dawkins, is the world of ideas, of beliefs, of cultures, of stories. It is the abstract, informational realm of the mind. These two systems are not separate. They are in a constant dynamic feedback loop. Our physical reality shapes our thoughts and beliefs, and our thoughts and beliefs, in turn, shape our physical reality. A new scientific theory, a meme, can lead to the development of a new technology that fundamentally alters our physical world. A powerful religious or political ideology can shape the course of history, leading to the rise and fall of empires. This interplay between the physical and the memic can be visualized in our dimensional framework. Our physical lives unfold along a specific four-dimensional timeline, a particular path through the fifth-dimensional possibility space. But our memic lives, the lives of our ideas and beliefs, are not so constrained. An idea can travel across time and space. It can connect different cultures. It can influence the choices that lead to the branching of different timelines. The memic system exists, in a sense, at a higher dimensional level, a level that can create interference patterns between the different potential realities of the physical world. A powerful shared belief, a dominant meme, can act as a kind of observer, collapsing the wave function of a collective reality, steering the course of a society or a civilization along a particular path. A cultural revolution, a scientific paradigm shift, a spiritual awakening. These are all moments where a new memic pattern creates a powerful interference effect, fundamentally altering the shape of our shared physical timeline. This concept of interference and overlap is not just a metaphor. It is a deep feature of the quantum world. The interference pattern in the double-slit experiment is a direct result of the overlap of the two possible paths of the electron's wave function. And in the higher dimensional reality of string theory, the properties of our universe are determined by the complex interference patterns of the vibrating strings as they move through the multidimensional Calabi-Yau space. Our experienced reality is an interference pattern, a product of the overlap and interaction of a vast number of underlying potential realities. We, as conscious beings, are the points at which this interference becomes manifest. We are both the product of our physical, four-dimensional reality, and the conduits for the higher dimensional, memic systems that flow through us. We are living at the intersection of worlds. This perspective gives us a new and powerful way to understand the tension between determinism and free will. Our physical bodies are subject to the deterministic laws of physics. Our lives are constrained by the circumstances of our birth, by the society we live in, by the history that has preceded us. This is the particle aspect of our being, but our minds, our consciousness, have access to the wave aspect, to the higher dimensional realm of possibility, of imagination, of choice. We have the freedom to introduce new ideas, new memes, into the system, to create new interference patterns, to choose which possibilities to collapse into our shared reality. Our free will is not the freedom to violate the laws of physics, but the freedom to navigate the possibility space that those laws allow. It is the freedom to choose which story to tell, which dream to follow, which future to create. The universe, in this view, is a vast information processing system, a cosmic computer that is constantly exploring its own infinite computational potential. And we, as conscious memic beings, are the universe's own agents of exploration, its own way of introducing novelty, of creating new patterns, of pushing the boundaries of what is possible. This brings us to a final, profound, and deeply humbling realization: the journey to understand the universe, from the smallest quantum flicker to the vastest cosmological structures, is not just a journey out there. It is also a journey in here. The same principles of superposition, of uncertainty, of entanglement, of dimensional overlap, that govern the cosmos are also at play in the deep, mysterious, and endlessly creative landscape of our own consciousness. The structure of the universe and the structure of the mind are not two separate things. They are reflections of each other, two different expressions of the same, underlying, informational reality. The cosmic web of galaxies and filaments is mirrored in the neural web of our own brains. The branching timelines of the multiverse are mirrored in the branching possibilities of our own choices. The creative power of the quantum vacuum is mirrored in the generative silence of our own deep, contemplative states. To study the universe is to study ourselves, and to study ourselves is to study the universe. We are not just in the cosmos is in us. This is the ultimate non-dual truth that lies at the heart of both the most ancient spiritual wisdom and the most advanced modern science. It is a truth that can be intellectually understood, but can only be truly known through direct, subjective experience. And the most universal and accessible portal to this experience is the nightly, sacred, and deeply mysterious journey of sleep. In sleep, we let go of our attachment to the collapsed, classical world of our waking identity, and we dissolve back into the quantum, superpositional, and multidimensional sea of pure potential. We become the universe, dreaming itself. We are the interference pattern between the seen and the unseen, the known and the unknown, the finite and the infinite. And in this beautiful, paradoxical, and life-giving dance, we find our true home, our true nature, and our true place in the grand, magnificent, and endlessly unfolding story of the cosmos. The concept of a 10-dimensional reality, while a cornerstone of advanced theoretical physics like string theory, remains one of the most challenging ideas for the human mind to grasp. Our entire evolutionary history has conditioned us to perceive and navigate a world of 3 spatial dimensions and 1 of linear time. To venture beyond this familiar framework requires a leap of imagination, a willingness to embrace abstraction, and a deep appreciation for the power of mathematics to describe realities that lie beyond the reach of our senses. The journey to the 10th dimension is a journey of conceptual scaffolding, building layer by layer, from the simple and intuitive to the complex and counterintuitive. We begin with the 0th dimension, a single, dimensionless point. It has no size, no extension, it is pure location. This is the ultimate abstraction, the conceptual seed from which all of geometry grows. From this point, we can extrude a line, creating the first dimension, the world of pure length. A being in this one-dimensional world could only move forward or backward along this line. The second dimension is created by adding a new direction, perpendicular to the first, creating a plane, a world of length and width. This is the world of flatland. The famous thought experiment proposed by the 19th century schoolmaster Edwin Abbott, the inhabitants of flatland. 2-dimensional shapes like squares and triangles can move left and right, forward and backward, but they have no concept of up or down. A 3-dimensional object, like a sphere, passing through their 2-dimensional world would appear as a mysterious and magical event, a point that grows into a circle, and then shrinks back to a point before disappearing completely. For the Flatlanders, the 3rd dimension is a realm of incomprehensible, godlike power. And this is a powerful analogy for our own relationship with the higher dimensions. We are the inhabitants of a 3-dimensional spaceland. By adding a 3rd direction, depth, we gain the world of solid objects, of volume, of the rich, physical reality we experience every day. But what if our 3-dimensional world is just a slice, a cross-section, of a higher dimensional reality, the 4th dimension? in the most common physical interpretation, is time, but it is not the flowing, transient time of our subjective experience. It is a spatialized time, a dimension along which the entire history of the three-dimensional universe is laid out. A four-dimensional being could perceive our entire lifespan, from birth to death, as a single, static, four-dimensional object, a space-time worm. They could see all the moments of our lives at once, just as we can see all the points on a line at once. This block universe view is a direct consequence of Einstein's theory of relativity, and it is a profoundly deterministic picture of reality. But the story does not end there. The fifth dimension, in the conceptual framework we are building, introduces the idea of possibility, of alternate realities. If every quantum event, every choice, causes the universe to split, then the fifth dimension is the space that contains all these branching, parallel timelines. A fifth-dimensional being could not only see our entire history, but could also see all the other possible histories that could have unfolded from the same starting point. They could see the you who took the other job, who married the other person, who made the other choice. The fifth dimension is the landscape of the might-have-beens. The sixth dimension takes this a step further. It is the plane that contains all of these possible histories, all of these branching timelines that arose from the specific initial conditions of our Big Bang, and it allows for a folding of this possibility space, a shortcut between different, seemingly distant branches. It is the complete phase space of our particular kind of universe. The seventh dimension marks a profound leap into an even greater level of abstraction. It is the dimension that contains the set of all possible universes that could have started with different initial conditions and different physical laws. This is the realm of the Level 2 multiverse of eternal inflation, a library of all possible cosmic beginnings. In one universe, gravity might be a repulsive force. In another, there might be 4 spatial dimensions. In a third, the speed of light might be different. The seventh dimension is the space that contains all these different and mutually inaccessible cosmic rulebooks. The eighth dimension is the plane that contains all of these different seventh-dimensional libraries, allowing for a branching, a comparison between these fundamentally different kinds of realities. The ninth dimension is the ultimate ensemble, the dimension that contains all possible physical laws, all possible initial conditions, all possible histories, all at once. It is the set of all possible universes, the complete catalog of all that is physically possible. And this brings us, finally, to the 10th dimension. In this hierarchical, conceptual model, the 10th dimension is the ultimate point of origin, the dimensionless, abstract point that contains, within it, all of the other, lower dimensions, and all of the infinite possibilities they represent. It is the point of everythingness, the ultimate ground of being from which all manifest reality, in all its infinite variety, unfolds. It is a concept that is almost pure metaphysics, a point where the language of physics and mathematics touches the language of mysticism and philosophy. But it is a concept that has a more concrete, if no less abstract, home in the framework of superstring theory. The mathematical consistency of superstring theory, the leading candidate for a theory of everything, requires a 10-dimensional space-time. In this theory, the fundamental constituents of reality are not point-like particles, but tiny, one-dimensional, vibrating strings. And the different ways these strings can vibrate, the different notes they can play, are what give rise to the different particles and forces we see in our universe. The properties of these vibrations are determined by the geometry of the 6 extra compactified dimensions. So, the 10th dimension, in this more physical picture, is the fundamental, underlying arena in which the cosmic symphony of the strings is played. The landscape of the 10 to the power of 500 possible vacuum states of string theory corresponds to the vast multidimensional possibility space we have been exploring. Each possible way of curling up the extra dimensions corresponds to a different possible universe, a different set of physical laws, a different symphony. Our universe is just one particular, beautiful, and life-bearing piece of music, played on the 10-dimensional instrument of the cosmos. This journey through the dimensions is a powerful exercise in expanding our own conceptual horizons. It is a journey that takes us from the familiar and the concrete to the abstract and the unimaginable. It is a journey that should instill in us a profound sense of humility, a recognition of the severe limitations of our own three-dimensional perception. And it is a journey that should also fill us with a sense of wonder, a wonder at the possibility that the reality we experience is just a thin, fragile, and beautiful membrane, a single slice of a much grander, much richer, and much more mysterious multidimensional cosmos. The 10th dimension, whether as a conceptual endpoint or a physical reality, is a powerful symbol of the infinite, creative potential that lies at the heart of existence, a potential that is both the source of our universe and the source of our own. Endless capacity to imagine, to question, and to explore. The participatory nature of reality, as suggested by the strange and beautiful world of quantum mechanics, is one of the most profound and revolutionary ideas in the history of human thought. It is an idea that challenges our most basic common sense assumptions about the world. And it is an idea that is still, a century after its birth, the subject of intense debate and a source of deep philosophical unease for many. The classical, Newtonian worldview, which has shaped our thinking for 300 years, is a worldview of a clockwork universe, a universe of solid, definite objects moving in a fixed, absolute space and time, governed by deterministic laws. It is a universe that exists out there, independent of our own minds, a universe that we can, in principle, observe and understand without affecting it. Quantum mechanics shatters this picture. It tells us that at the fundamental level, reality is not a collection of definite things, but a web of interconnected probabilities. A particle does not have a definite position or a definite momentum until it is measured. It exists in a superposition of all possible states, a wave function that describes the probability of finding it here or there or with this momentum or that one. And it is the very act of measurement, of observation, that seems to be the mysterious ingredient that collapses this wave of probability into a single, definite reality. This is the observer effect, the strange and unsettling fact that the world we see seems to be, in some deep and fundamental way, shaped by the very act of our seeing it. This has led to a host of perplexing questions and a zoo of different interpretations. Does this mean that we are literally creating reality with our minds? The answer for most physicists is a qualified no. The observer effect is not about a mystical power of consciousness to will things into being. It is a consequence of the fact that any act of measurement, any interaction with a quantum system, is a physical process that necessarily disturbs that system. To measure an electron, you have to bounce a photon off of it, and this interaction inevitably changes its state. In this view, the observer does not need to be a conscious being. A simple, inanimate particle detector is enough to cause the wave function to collapse, but this just pushes the mystery back a step. What is it about the interaction with a macroscopic, classical measuring device that is so special? Why does it have the power to collapse the quantum superposition? This is the heart of the measurement problem, and it is a problem that has not been definitively solved. The decoherence program has provided a partial answer, showing how a quantum system rapidly loses its superpositional nature as it becomes entangled with the vast number of degrees of freedom in its environment. But decoherence does not explain which specific outcome is chosen from the initial superposition. It just explains why we do not see macroscopic superpositions. The many worlds interpretation offers a radical and elegant way out of this puzzle. It simply denies that the collapse ever happens. The wave function is the complete and total description of reality, and it always evolves in a smooth, deterministic way according to the Schrödinger equation. When a measurement is made, the universe does not collapse into a single state. It branches. The observer becomes entangled with the system, and the entire world splits into multiple parallel realities, one for each possible outcome. In one branch, the electron is found at position A. In another, it is found at position B. There is a version of you that experiences each outcome. In this view, we are not collapsing reality. We are simply experiencing one particular branch of a vast and constantly splitting quantum multiverse. This is a breathtakingly grand and logically consistent picture, but it comes at the price of accepting an almost unimaginable ontological extravagance and infinite number of parallel, unobservable worlds. But regardless of which interpretation one prefers, the central, participatory nature of the quantum world remains. We are not detached spectators of a pre-existing reality. We are entangled participants in a cosmic drama, a drama where the questions we ask, the measurements we make, the choices we take, all play a crucial role in shaping the reality that unfolds. This has a powerful and direct parallel in our own subjective lives. The reality we experience is not a passive reception of external data. It is an active, co-creative process. Our beliefs, our expectations, our attention, all act as a kind of filter, collapsing the infinite, superpositional potential of the world into a single, experienced reality. If we believe the world is a hostile and dangerous place, we will tend to notice and amplify the evidence that confirms this belief. If we believe the world is a place of beauty and opportunity, we will tend to experience a reality that reflects this. Our consciousness is not just a mirror reflecting the world. It is also a lamp that illuminates it, and in illuminating it helps to bring it into being. This does not mean that we have absolute, solipsistic control over reality. We are still bound by the underlying probabilistic laws of the wave function, both in the physical world and in our own psyches. But we do have a choice. We have the choice of where to direct our attention, which questions to ask, which possibilities to engage with. And this choice is a creative, world-shaping act. This is the deep and beautiful truth that the participatory universe reveals to us. It is a truth that calls us to a new level of responsibility, a new level of conscious participation in the ongoing creation of our own lives and of our shared world. And it is a truth that can be most profoundly felt in the quiet, creative, and dreamlike spaces of our own inner world, a world where we are, at every moment, both the artist and the canvas, the observer and the observed, in the grand, magnificent, and endlessly unfolding masterpiece of reality. Imagine a white dwarf, a cosmic ember, one of the universe's most intriguing leftovers from a star's long and luminous life. This small, incredibly dense object is the final, quiescent form of a star like our sun. Though it is packed with a mass comparable to our star, it has been squeezed into a volume no larger than the Earth. It shines faintly, a ghost of its former self, slowly cooling over billions and billions of years, a diamond in the cosmic graveyard. A white dwarf is a marvel of stability, held together by a strange and powerful quantum mechanical force called electron degeneracy pressure. This is a force that arises from one of the most fundamental principles of the quantum world, the Pauli exclusion principle. which dictates that no two electrons can occupy the same quantum state in the same place at the same time. As the core of a dying star collapses under its own immense gravity, its electrons are forced closer and closer together into higher and higher energy states. This creates a powerful outward pressure, a quantum resistance to being squeezed that ultimately halts the gravitational collapse and holds the white dwarf up against its own weight. These stellar remnants are incredibly stable, some of the most reliable and predictable objects in the entire cosmos. But even they have their limits. And it is at these limits, at the very edge of stability, that some of the most profound and violent dramas of the universe unfold. This is where the Chandrasekhar limit comes into play, a critical tipping point discovered by the Indian-American astrophysicist Subrahmanyan Chandrasekhar. This limit defines the maximum mass that a white dwarf can have and still be supported by electron degeneracy pressure. That limit is about 1.4 times the mass of our Sun. If a white dwarf, through some cosmic circumstance, manages to accumulate more mass than this, if it crosses this critical threshold, it is in deep trouble. The inward pull of gravity will overwhelm the outward push of the quantum pressure, and the star will begin a new, catastrophic collapse. At this tipping point, the white dwarf is destined to become something even stranger, even more extreme. It might collapse into a neutron star, an object so dense that a single teaspoon of its matter would weigh billions of tons. Or, if it is massive enough, it might transform into the universe's ultimate monster, a black hole, a region of space-time where gravity is so strong that not even light can escape. But whether this collapsing star becomes a neutron star or a black hole, our current theories of physics are pushed to their breaking point. The moment of collapse is a place where the two great pillars of modern physics, Einstein's general theory of relativity and the theory of quantum mechanics, collide in a spectacular and, as yet, unresolved conflict. General relativity, our theory of the large scale, tells us that the collapsing matter should form a singularity, a point of infinite density and zero volume, where space-time itself is infinitely curved. But quantum mechanics, our theory of the small scale, tells us that the very concept of a point is meaningless, that the uncertainty principle should prevent such an infinite localization. To understand what truly happens at this ultimate frontier of reality, we need a new theory, a theory that can bridge the gap between the smooth, geometric world of Einstein and the fuzzy, probabilistic world of the quantum. We need a theory of quantum gravity. This is the holy grail of modern theoretical physics, the quest for a single, unified framework that can describe the universe at all scales, from the gentle dance of the planets to the violent heart of a collapsing star. In the 17th century, a scientific revolution began to unfold, a revolution that would forever change our understanding of the cosmos. Scientists and philosophers, driven by a deep and insatiable curiosity, started to ask big, fundamental questions about the nature of space and time. They sought to peel back the veil of everyday experience and to glimpse the underlying mathematical order of the universe. The prevailing view at the time, the one that had been handed down from the great Greek philosopher Aristotle, was that of a dressed space, a space that was always filled with some kind of substance. The idea of a true, empty vacuum was considered a logical absurdity. But a new generation of thinkers, armed with new mathematical tools and a new experimental spirit, began to challenge these long-held assumptions. Galileo Galilei, with his improved telescope, revealed a universe that was far vaster and more complex than the tidy, Earth-centered cosmos of the scholastics. His meticulous experiments on motion and mechanics laid the groundwork for a new, quantitative science of the physical world. And although he died in despair, His legacy was carried forward by a man who was born in the very same year of his death. Isaac Newton. In 1687, Newton published his monumental work, the Philosophiae Naturalis Principia Mathematica, a book that would become the foundation of classical physics for the next 2 centuries. In it, Newton laid out his 3 laws of motion and his law of universal gravitation, a single, elegant equation that described the force that governs the fall of an apple and the orbit of the moon. But to make this beautiful mathematical machinery work, Newton had to make a profound and deeply philosophical assumption. He had to assume the existence of an absolute space and an absolute time. For Newton, space was an infinite, eternal, and unchanging container, a fixed, 3-dimensional stage upon which the cosmic drama played out. And time was a universal, relentless clock, ticking at the same rate for all observers everywhere in the universe. This was the world of undressed space, a world where the void was real. In this classical, Newtonian view, if you were to remove all the matter and all the energy from the universe, this empty container of absolute space and time would still exist, a silent and eternal backdrop waiting for a new story to begin. This idea, while powerful and successful, raises deep philosophical questions. If the universe is everything that exists, how can it exist within something else? It is like trying to imagine a God's eye view of the cosmos, a perspective from outside of reality itself, a perspective that is, by its very nature, impossible for us to grasp. These are not just abstract philosophical games. They force us to examine the very foundations of our knowledge, to distinguish between what we can observe and what we must assume. We never truly see absolute space or absolute time. All motion is relative. An object is at rest only in relation to another object. The coordinate systems we use to map the world, the familiar X, Y, and Z axes, are entirely arbitrary human conventions. And yet, for Newton, the assumption of an absolute, unchanging framework was a necessary one. It was the only way he could make sense of concepts like acceleration and rotation. An object is accelerating not relative to another object, but relative to absolute space itself. But by the end of the 19th century, a new revolution was brewing, one that would challenge the very foundations of Newton's absolute universe. And it began not with gravity, but with the mysterious forces of electricity and magnetism. In the mid-19th century, a self-taught English scientist named Michael Faraday, a man with a little formal education but a profound and intuitive grasp of the physical world, began to unravel the deep and hidden connection between electricity and magnetism. Through a series of brilliant and simple experiments, he showed that a moving magnet could generate an electric current in a wire, and that an electric current could, in turn, create a magnetic field. These were 2 sides of the same fundamental coin. To describe these phenomena, Faraday, lacking the mathematical language of his contemporaries, developed a powerful and intuitive new concept, the field. He imagined space as being filled with invisible lines of force, a web of influence that stretched out from electric charges and magnets. An object doesn't just feel a force at a distance, it responds to the field at its location. Even Newton's theory of gravity could be rephrased in this language, with the Earth moving through the Sun's gravitational field. But it was Faraday's work on electricity and magnetism that truly established the field as a central concept in physics. It was a concept that would be given its definitive mathematical form by the brilliant Scottish physicist, James Clerk Maxwell. In a series of papers published in the 1860s, Maxwell synthesized all the known phenomena of electricity and magnetism into a single, elegant set of 4 equations. These equations revealed a deep and beautiful symmetry, A changing electric field creates a magnetic field, and a changing magnetic field creates an electric field. Maxwell realized that this interplay would create a self-sustaining, traveling wave of oscillating electric and magnetic fields, a wave that would propagate through space. And when he calculated the speed of this wave from the fundamental constants of his theory, he found a number that was astonishingly familiar: 300,000 kilometers per second, the speed of light. In a moment of profound insight, Maxwell realized that light itself is an electromagnetic wave. This was one of the greatest unifications in the history of science, a moment that revealed a deep and hidden connection between two seemingly disparate phenomena. But this triumph also created a new and profound puzzle. Waves, as they were understood at the time, always needed a medium to travel through. Sound waves travel through air, ocean waves travel through water. So, what was the medium for light waves? What was the ether that was waving? Physicists imagined a subtle, all-pervading, luminiferous ether that filled all of space and acted as the stationary, absolute reference frame against which the speed of light should be measured. But when scientists, like Albert Michelson and Edward Morley, conducted a series of incredibly precise experiments to try and detect the motion of the Earth through this ether, they found nothing. The speed of light was the same in all directions. Regardless of the Earth's motion, the ether did not seem to exist. This was a profound crisis for physics. Newton's laws seemed to require an absolute space. Maxwell's theory seemed to require a stationary ether, and experiments showed no evidence for either. The stage was set for a new revolution, a revolution that would be ignited by a young unknown patent clerk in Bern, Switzerland. In 1905, Albert Einstein, with a boldness and a clarity of thought that was breathtaking, cut through the confusion. He proposed that we should abandon the search for an ether and instead take the experimental results at face value. He elevated two simple principles to the status of fundamental postulates. First, the principle of relativity. The laws of physics are the same for all observers who are in uniform motion. There is no privileged, absolute state of rest. And second, the principle of the constancy of the speed of light. The speed of light in a vacuum is the same for all observers, regardless of the motion of the light source or the observer. From these two seemingly simple postulates, Einstein deduced a series of profound and world-altering consequences. He showed that there can be no such thing as absolute simultaneity, that two events that appear to happen at the same time for one observer can happen at different times for another. This meant that there could be no absolute, universal time. Time itself is relative. He showed that for a moving observer, time runs slower and distances get shorter, a phenomenon known as time dilation and length contraction. And in a short addendum to his paper, published later that year, he showed that mass and energy are two different aspects of the same fundamental entity, linked by the most famous equation in all of science, E equals mc squared. The energy bound up in even a tiny amount of mass is immense. This is the equation that explains why the sun shines, and it is the equation that would later unleash the terrible power of the atomic bomb. Einstein's special theory of relativity was a stunning achievement, but it was incomplete. It dealt only with observers in uniform motion. It could not handle acceleration, and it was still incompatible with Newton's theory of gravity, which described a force that seemed to act instantaneously across vast distances, a clear violation of the new cosmic speed limit set by the speed of light. Einstein knew his revolution was only half finished. He would spend the next decade of his life grappling with the problem of gravity, a journey that would lead him to an even deeper and more beautiful understanding of the nature of space and time. The early 20th century was a time of unprecedented intellectual ferment, a period that saw not one, but two fundamental revolutions in our understanding of the physical world. While Einstein was busy dismantling the classical, Newtonian concepts of absolute space and time, another equally profound revolution was taking place in the heart of Europe, a revolution that would reveal the strange, probabilistic, and deeply counterintuitive nature of reality at the smallest scales. This was the birth of quantum mechanics. The story begins in 1900 with the German physicist Max Planck, while trying to solve a puzzle related to the nature of the light emitted by hot objects, a problem known as the blackbody radiation problem. Planck was forced to make a radical and desperate assumption. He proposed that energy is not a continuous quantity, but is emitted and absorbed in discrete, tiny packets, which he called quanta. This was a revolutionary idea, one that went against all the principles of classical physics, and even Planck himself was deeply uneasy with it. But it was a young Albert Einstein who, in 1905, his miracle year, took Planck's idea and ran with it. He proposed that light itself is not a continuous wave, but is composed of these tiny, indivisible bundles of energy, which we now call photons. This was the birth of the wave-particle duality, the idea that light can behave both like a wave and like a particle, a concept that would become a central and enduring paradox of the quantum world. Building on this idea, the French physicist Louis de Broglie, in 1923, made an even bolder leap. He hypothesized that if waves like light can behave like particles, then perhaps particles like electrons should also behave like waves. This was a stunning and audacious proposal, and it was soon confirmed by experiment. The double-slit experiment, which had long been used to demonstrate the wave-like nature of light, was now performed with electrons, and to everyone's astonishment, it worked. A single electron, fired at a barrier with two slits, seemed to pass through both slits at once, creating an interference pattern on the detector screen. The unmistakable signature of a wave. This wave-particle duality is at the heart of the quantum mystery. An electron is not a little billiard ball, nor is it a simple wave. It is something else entirely. A quantum entity that exhibits both wave-like and particle-like properties, depending on how we choose to measure it. This led to the development of the wave function, a mathematical object that describes the probability of finding a particle at any given point in space. Before a measurement is made, the particle exists as a superposition of all possible states, a cloud of probability. The moment a measurement is made, this wave function collapses, and the particle is found at a single, definite location. This concept of the collapse of the wave function was deeply troubling to Einstein. It seemed to suggest that the act of observation itself was what brought reality into being, and it also seemed to imply a kind of instantaneous, spooky action at a distance that violated the principles of his own theory of relativity. He famously expressed his dissatisfaction with the probabilistic nature of the theory, declaring, "God does not play dice." But the experimental evidence was undeniable. The quantum world is a world of probabilities, of uncertainty, of superposition. The Danish physicist Niels Bohr, who became the philosophical leader of the quantum revolution, argued that we should simply accept this weirdness as a fundamental feature of nature. His Copenhagen interpretation of quantum mechanics, developed in collaboration with Werner Heisenberg, proposed that our classical concepts of wave and particle are just complementary and mutually exclusive ways of describing the quantum world. We can perform an experiment that reveals the particle nature of an electron, or we can perform an experiment that reveals its wave nature, but we can never do both at the same time. The question, what is an electron really, is, in this view, a meaningless one. It is only in the context of a specific experimental setup that the electron's properties become definite. This is the principle of complementarity, and it is deeply connected to Heisenberg's uncertainty principle, which places a fundamental limit on what we can know about the quantum world. The debate between Einstein, with his desire for a deeper deterministic and locally real theory, and Bohr, with his embrace of uncertainty, complementarity, and the central role of the observer, was one of the great intellectual duels of the 20th century. While Einstein's intuition led to some of the most powerful thought experiments in the history of physics, such as the EPR paradox, which highlighted the spooky nature of quantum entanglement, it was Bohr's interpretation that ultimately seemed to be borne out by experiment. The universe, at its deepest level, does not seem to care about our classical, common-sense intuitions. It is a world of strange and beautiful paradoxes, a world where a particle can be in many places at once, where the future can influence the past, and where the very act of looking at something seems to change what is there. It is a world that is far stranger and far more mysterious than any of our classical theories could have ever imagined. The quest to build a quantum theory of the fundamental forces of nature was one of the great triumphs of 20th century physics. It was a journey that took the strange and counterintuitive principles of quantum mechanics and applied them to the classical field theories of Maxwell and others, resulting in a new and powerful framework known as quantum field theory. But boy, this is the language in which our modern standard model of particle physics is written. In QFT, the fundamental reality is not particles, but fields. There is an electron field, a quark field, a photon field, and so on. And these fields permeate all of space-time. The particles we observe are just the quantized excitations, the ripples, the vibrations of these underlying fields, and the forces between these particles are not a spooky action at a distance, but are mediated by the exchange of other particles, the force-carrying or messenger particles. In the case of the electromagnetic force, this messenger particle is the photon. When two electrons repel each other, they are not directly pushing on each other. They are exchanging virtual photons, like two ice skaters throwing bowling balls at each other. The recoil from throwing and catching the bowling balls pushes the skaters apart. In the same way, the exchange of virtual photons mediates the electromagnetic force. This framework was first developed for the electromagnetic force in the 1940s in a theory known as quantum electrodynamics. It was a stunningly successful theory, making predictions that have been experimentally verified to an incredible degree of precision. It was later extended to the other two fundamental forces of the Standard Model, the weak nuclear force and the strong nuclear force. The weak force, which is responsible for certain types of radioactive decay, is mediated by heavy messenger particles called the W and Z bosons. The strong force, which binds quarks together inside protons and neutrons and holds the atomic nucleus together, is mediated by massless particles called gluons. All of these forces, and all of the matter particles they act upon, are described with breathtaking accuracy by the Standard Model. And at the heart of this model lies a deep and beautiful principle, the principle of gauge symmetry. A gauge symmetry is a kind of mathematical redundancy in our description of a physical system. It means that we can change or transform the underlying quantum fields in a certain way at every point in space-time, and the physical predictions of the theory will remain exactly the same. The universe, it seems, has a deep underlying symmetry. But here is the crucial insight, first developed by Hermann Weyl and later by Chen-Ning Yang and Robert Mills. If you demand that a theory has a particular gauge symmetry, then the existence of a corresponding force, mediated by a messenger particle, becomes a mathematical necessity. The force is required to keep the physics unchanged under the symmetry transformation. The electromagnetic force, for example, is a necessary consequence of a gauge symmetry known as U symmetry. The strong force is a consequence of SU symmetry, which is related to the color charge of quarks, and the weak force, along with electromagnetism, is a consequence of a combined SU-XU symmetry. This is a profound and powerful idea. It suggests that the forces of nature are not arbitrary, but are a necessary consequence of the deep, underlying mathematical symmetries of the universe. It is a vision of a cosmos that is not just a random collection of particles and forces, but is governed by a deep, elegant, and unifying mathematical logic. This vision, however, has one glaring omission: gravity. The great dream of 20th century physics was to find a similar quantum field theory description of gravity, to find the gauge symmetry that gives rise to the gravitational force, and to identify its messenger particle, the hypothetical graviton. But this quest has proven to be incredibly difficult. When physicists try to apply the standard techniques of quantum field theory to Einstein's theory of general relativity, the mathematics breaks down. The calculations are plagued by uncontrollable, infinite results, a sign that the theory is incomplete. The problem lies in the fundamentally different nature of gravity. In the standard model, the other forces are actors on a fixed, static stage of space-time. But in general relativity, gravity is the stage. It is the dynamic, curving geometry of space-time itself. To quantize gravity is to quantize space-time, and this is where the trouble begins. At the incredibly small sub-Planck length scales, the uncertainty principle of quantum mechanics implies that space-time itself should be a chaotic, roiling quantum foam of violent fluctuations. The smooth, geometric picture of general relativity breaks down completely. The two great pillars of modern physics, general relativity and quantum mechanics, which work so perfectly in their own domains, seem to be fundamentally, irreconcilably, at war with each other at the ultimate frontier of reality. The resolution of this deep and profound conflict is the central challenge of 21st century theoretical physics, and it is a challenge that has led to some of the most ambitious, most beautiful, and most speculative ideas in the history of science. Ideas like string theory, the dream of a unified theory, a single framework that could encompass all the forces and particles of nature, including gravity, has been the driving force of fundamental physics for the better part of a century. And for the last few decades, the most promising and most controversial candidate for such a theory has been string theory. It is a theory of breathtaking ambition and profound mathematical elegance, and it proposes a radical and fundamental shift in our understanding of reality. At its core, string theory's proposal is simple. The fundamental constituents of the universe are not point-like, zero-dimensional particles, but tiny, one-dimensional, vibrating strings of energy. These are not strings in the ordinary sense. They are unimaginably small, with a characteristic length of around the Planck length, 10 to the power of minus 33 centimeters. If an atom were magnified to the size of the observable universe, one of these strings would be about the size of a tree. In this picture, the rich and diverse zoo of elementary particles that we observe in nature, the quarks, the leptons, the photons, the gluons, are not different things. They are all made of the same fundamental stuff, a single vibrating string. The differences between the particles arise from the different ways that these strings can vibrate. Just as the string of a violin can vibrate in different patterns to produce different musical notes, a C, a G, and E-flat, so too can the fundamental strings of the universe vibrate in different modes to produce the different particles we see. An electron is a string vibrating in one pattern. A photon is a string vibrating in another. A quark is a string vibrating in yet another. The properties of these particles, their mass, their electric charge, their spin, their other force charges, are all determined by the precise, resonant pattern of the string's vibration. This is a unification of unprecedented power and beauty. All the matter and all the forces of nature are brought under a single, unifying umbrella. The universe, in this view, is a cosmic symphony, a rich and complex harmony played out on the vibrating strings of reality. The laws of physics are the rules of harmony, the principles that govern which notes can be played. And the universe we inhabit is the particular, beautiful, and complex piece of music that has been composed from these fundamental notes. One of the most remarkable and compelling features of string theory is that gravity is not an optional extra. It is a necessary and unavoidable consequence of the theory. Among the infinite number of possible vibrational patterns of the string, there is one that has the precise properties of the hypothetical graviton, the quantum particle that is thought to mediate the force of gravity. String theory does not just accommodate gravity, it demands it. This was a stunning and unexpected discovery, and it is one of the primary reasons why so many physicists have been drawn to the theory. But this beautiful unifying picture comes with a set of extraordinary and challenging consequences. The first is that, for the theory to be mathematically consistent, it requires the existence of extra hidden dimensions of space. The world we perceive has 3 spatial dimensions and 1 of time. But string theory predicts that the universe actually has 9 or 10 spatial dimensions, for a total of 10 or 11 space-time dimensions. The extra 6 or 7 dimensions are not something we can see or experience directly. They are thought to be compactified, curled up into a tiny, complex, geometrical shape at every point in our familiar 3-dimensional space. The geometry of these extra dimensions is not just a mathematical curiosity. It is the key to the theory's predictive power. The precise shape and size of this Calabi-Yau manifold determines the possible vibrational patterns of the strings, and therefore, it determines the entire spectrum of particles and forces that we observe in our universe. The laws of physics are a reflection of the geometry of these hidden dimensions. The second major challenge is the landscape problem, string theory. It turns out, does not predict a unique geometry for the extra dimensions. It allows for a vast, and possibly infinite, number of different stable Calabi-Yau manifolds, each corresponding to a different vacuum state, a different set of physical laws. This has led to the idea of the string theory landscape, a multiverse of at least 10 to the power of 500 different possible universes. This is a source of great debate and controversy within the physics community. For some, it is a fatal flaw, a sign that the theory is not truly predictive. For others, it is the theory's greatest strength, providing a natural home for the anthropic principle and an explanation for the apparent fine-tuning of our own universe. And finally, there is the challenge of experimental verification. The energies required to directly probe the Planck scale and to see the string-like nature of particles are many orders of magnitude beyond the reach of our current or foreseeable technology. This has led to the criticism that string theory is not a true scientific theory, but a form of mathematical philosophy. But the proponents of string theory are not deterred. They argue that the theory's internal consistency, its mathematical beauty, and its ability to unify gravity and quantum mechanics are strong indications that it is on the right track. And they are actively searching for indirect, low-energy consequences of the theory that might be testable, such as the existence of supersymmetric particles, the precise pattern of neutrino masses, or subtle signatures in the cosmic microwave background. String theory is still very much a work in progress, a beautiful and ambitious mathematical framework that is still searching for its definitive physical form. But it represents our boldest and most profound attempt yet to read the mind of God, to find the single, elegant equation that can describe the entire magnificent symphony of the cosmos. The fundamental conflict between the two great pillars of modern physics, general relativity and quantum mechanics, becomes most acute at the very smallest of scales. General relativity, with its vision of a smooth, continuous, and dynamic space-time, works beautifully for describing the large-scale structure of the universe. But when we try to zoom in, to look at the fabric of space-time at the Planck length, the uncertainty principle of quantum mechanics tells us that this smooth picture must break down. At these incredibly small distances, the zero-point energy of the gravitational field itself would lead to violent, chaotic quantum fluctuations in the very geometry of space and time. This is the quantum foam, a roiling, turbulent sea of virtual black holes and wormholes, where the concepts of distance and duration lose their meaning. The combination of the equations of general relativity and quantum mechanics in this regime leads to nonsensical infinite results, a clear sign that our theories are incomplete. String theory offers a radical and elegant solution to this problem. By replacing the zero-dimensional, point-like particles of our conventional theories with one-dimensional, extended strings, the theory effectively smears out the interactions between them. In a point-particle theory, an interaction happens at a single, infinitely small point in space-time. This is what leads to the problematic infinities. But in string theory, an interaction is no longer a single point. When two strings collide, they merge and split over a small, but finite, region of space-time. The interaction is smeared out, and this smearing has a profound effect. It softens the violent, short-distance quantum fluctuations of space-time. It tames the quantum foam, and it eliminates the problematic infinities that have plagued all previous attempts to build a quantum theory of gravity. The strings are too large to be sensitive to the sub-Planck scale chaos. It is like trying to feel the microscopic bumps on a polished granite surface with your finger. Your finger is too large. It averages over the bumps, and the surface feels smooth. In the same way, the strings average over the quantum foam, and they experience a smooth, well-behaved space-time. This is a profound and beautiful insight. It suggests that the very existence of a minimum size for the fundamental constituents of nature, the fact that they are strings and not points, is what saves the universe from the mathematical pathologies of an infinitely chaotic quantum space-time. String theory, in this sense, sets a fundamental limit to the resolution with which we can probe the universe. There is a minimum length, on the order of the Planck length, below which the very concept of distance becomes meaningless. This is not a limitation of our technology. It is a fundamental feature of reality as described by the theory. This idea of a minimum length has been explored in other approaches to quantum gravity as well, and it is a recurring theme in the search for a unified theory. It suggests that the continuous, infinitely divisible space-time of classical physics is an illusion, an approximation that breaks down at the ultimate frontier of reality. But the beauty of string theory is that this minimum length is not an ad hoc assumption. It is a direct and necessary consequence of the theory's internal mathematical consistency. And this resolution of the conflict between general relativity and quantum mechanics is not the only triumph of the theory. It also, as we have seen, provides a natural home for a zoo of other higher dimensional objects known as brains. In the mid-1990s, in what has been called the second superstring revolution, physicists discovered that the 5 seemingly different, consistent string theories that had been developed were actually just different aspects of a single, underlying 11-dimensional theory, known as M-theory. In this deeper, more mysterious theory, strings are not the only fundamental objects. There are also 2-dimensional membranes, 3-dimensional volumes, and so on, up to 9-dimensional 9-branes. Our entire observable universe could be a 3-brane, a vast three-dimensional membrane floating in a higher dimensional, 11-dimensional bulk space. This brain world scenario opens up a host of new and exciting possibilities. It could explain the weakness of gravity. It could provide a home for dark matter. And it could lead to new cyclical models of the cosmos. The journey into the heart of string theory is a journey into a world of incredible mathematical beauty, of hidden dimensions, of vibrating strings and higher dimensional brains. It is a world that is far removed from our everyday experience, a world that is still shrouded in deep mystery and profound, unanswered questions. But it is a world that may hold the key to the ultimate unification of all the laws of nature, the key to a final, complete, and beautiful understanding of the deep, string-like music of the cosmos. The existence of extra hidden dimensions of space is one of the most striking and counterintuitive predictions of string theory, and yet it is a necessary one. The mathematics of the theory simply does not work in our familiar three spatial dimensions. The calculations are plagued by nonsensical, negative probabilities and other mathematical inconsistencies. It is only when the strings are allowed to vibrate in 9 spatial dimensions that these inconsistencies magically cancel out, and a consistent, well-behaved quantum theory emerges. This is a powerful and deeply mysterious constraint. It is as if the universe itself is telling us, through the language of mathematics, that the reality we perceive is not the whole of reality. But if these extra dimensions exist, where are they, and why don't we see them? The answer, first proposed by Theodore Kaluza and Oscar Klein in the 1920s in a different context, is that the extra dimensions are compactified, or curled up, into a tiny subatomic size. Imagine a long, thin straw. From a great distance, it appears to be a one-dimensional line. But as you get closer, you realize that at every point along the line, there is a second circular dimension that you can travel around. The extra dimensions of string theory are thought to be like this circular dimension of the straw, but far, far smaller, curled up on a scale of around the Planck length. They are so small that they are completely inaccessible to our senses and even to our most powerful particle accelerators. We are like giants, lumbering through a three-dimensional world, completely unaware of the tiny, intricate, six-dimensional geometry that exists at every single point in the space around us. But these hidden dimensions are not just a mathematical curiosity. They are the key to the theory's predictive power. The geometry of these extra dimensions, the precise way in which they are curled up and twisted, determines the allowed vibrational patterns of the strings. And since the vibrational patterns of the strings determine the properties of the particles we observe, it means that the entire physics of our universe, the masses of the quarks and leptons, the strengths of the fundamental forces, the number of particle families, is a direct consequence of the geometry of these hidden six-dimensional spaces. The laws of nature are a reflection of the shape of the universe's extra dimensions. This is a stunning and profound idea. It suggests that the answers to some of the deepest questions in particle physics. Why are there 3 families of particles? Why do they have the masses they do? Are not to be found in the particles themselves, but in the geometry of a higher dimensional space. The search for the fundamental laws of physics becomes a search for the correct Calabi-Yau manifold, the specific type of six-dimensional, complex geometrical shape that is required by the consistency of string theory. The problem is that there are a vast number of possible Calabi-Yau manifolds, perhaps as many as 10 to the power of 500, each corresponding to a different, consistent set of physical laws. This is the landscape problem, and it is one of the greatest challenges facing string theory. If the theory allows for such a vast number of possible universes, how can it ever make a unique, falsifiable prediction for our own? The answer, for some, lies in the anthropic principle and the multiverse. But for others, it is a sign that our understanding of the theory is still incomplete, that there must be some as yet undiscovered principle that selects a unique Calabi-Yau manifold, a unique set of physical laws, for our universe. The question of why our universe has 3 large, extended spatial dimensions and 6 tiny, curled-up ones is another deep and unsolved mystery. Some cosmological models have proposed that in the very early universe, all the dimensions may have started out small and curled up, and that some dynamical process, perhaps related to cosmic inflation, caused 3 of them to rapidly expand to their current vast size, while the others remain trapped at the Planck scale. These are all ideas that are on the cutting edge of theoretical physics, ideas that are pushing the boundaries of our mathematics and our imagination. But they all point to the same remarkable conclusion that the world we see, the familiar world of 3 spatial dimensions, may just be a slice, a projection, of a much richer, much deeper, and much more complex higher dimensional reality. And that the secrets of our own familiar world may be hidden in the beautiful, intricate, and invisible geometry of the universe's other, hidden dimensions. The quest for a final unified theory of everything, a quest epitomized by string theory, is one of the grandest and most ambitious endeavors in the history of human thought. And yet, it is an endeavor that is not without its critics. The very idea of a theory of everything can seem arrogant, a hubristic attempt to put the infinite, mysterious universe into a neat, tidy, and finite human-made box. And string theory, in particular, has faced a growing chorus of criticism in recent years, not just from philosophers, but from within the physics community itself. The criticisms are varied and powerful. Some argue that the theory's reliance on mathematical beauty as a guide to truth is a dangerous and potentially misleading path. The history of science is littered with beautiful, elegant theories that turned out to be wrong. Kepler's beautiful, Platonic model of the solar system, with the planetary orbits inscribed within a nested series of regular polyhedra, was a mathematical masterpiece. But it had nothing to do with the way the solar system actually works. The physicist Paul Dirac famously said that it is more important to have beauty in one's equations than to have them fit experiment. But the physicist Sabine Hossenfelder, in her book Lost in Math, has argued that this modern obsession with mathematical beauty has led a generation of theoretical physicists down a rabbit hole of elegant, but ultimately untestable and physically irrelevant ideas. The primary and most potent criticism of string theory is precisely this, its lack of testability. The theory's fundamental predictions, such as the existence of strings, extra dimensions, and a whole host of new supersymmetric particles, are all at the Planck scale, an energy regime that is a quadrillion times higher than anything we can reach with our current particle accelerators. Building an accelerator powerful enough to directly probe this scale would require a machine the size of our galaxy. In the absence of direct experimental evidence, how can we ever know if the theory is right? How can it be distinguished from a beautiful but purely mathematical fantasy? The theory's defenders argue that this criticism is unfair. All scientific theories, they say, have a domain of applicability. And it is not a flaw in a theory if its direct predictions lie beyond our current technological reach, and they point to the possibility of indirect evidence. The existence of supersymmetry, for example, is a generic prediction of most string theory models, and the discovery of supersymmetric particles at the Large Hadron Collider would be a major circumstantial piece of evidence in the theory's favor. The fact that no such particles have yet been found has been a major disappointment for the field. Another avenue for indirect evidence could be cosmology, The precise details of cosmic inflation, the statistical properties of the cosmic microwave background, the nature of dark matter and dark energy, all of these could hold subtle clues, faint fingerprints of an underlying stringy reality, the discovery of a fundamental particle that makes up dark matter, for example, and the measurement of its properties could provide a crucial test of the predictions of different string theory models. The debate over the scientific status of string theory is a healthy and necessary one. It forces the theory's proponents to be more rigorous, to search for more testable predictions, and to confront the theory's deep conceptual challenges, like the landscape problem. And it forces the theory's critics to acknowledge its immense theoretical power, its mathematical beauty, and its remarkable ability to unify the seemingly disparate worlds of gravity and quantum mechanics. The quest for a theory of everything is a journey into the unknown, a journey that is fraught with uncertainty, with controversy, and with the very real possibility of failure. But it is a journey that is driven by one of the deepest and most noble of all human impulses, the desire to understand, to find a sense of order and meaning in a vast and often chaotic universe, to read the mind of God. Whether string theory is the final chapter in this long and beautiful story, or just another fascinating and ultimately incorrect chapter, remains to be seen. But the quest itself, the bold and courageous attempt to grasp the ultimate nature of reality, is a testament to the incredible power and the incredible beauty of the human mind. The revolution in our understanding of the cosmos that was ignited by Einstein's theories of relativity is a story of profound and counterintuitive insights into the nature of space, of time, and of gravity. And yet, for all its power and beauty, general relativity is an incomplete theory. It is a classical theory, a theory that does not incorporate the strange and wonderful principles of the quantum world. This incompleteness becomes a critical failure at the very heart of the theory's most dramatic predictions, the singularity at the beginning of the Big Bang and the singularity at the center of a black hole. These are points where the theory predicts that the density of matter and the curvature of space-time become infinite, a clear sign that the theory itself has broken down and is no longer applicable. To understand these ultimate frontiers of reality, we need a quantum theory of gravity. And one of the most promising and well-developed approaches to this profound challenge is loop quantum gravity. Unlike string theory, which starts with particles and forces and finds that gravity is a necessary consequence, LQG starts with space-time itself, with the very fabric of Einstein's general relativity, and attempts to quantize it directly, using the principles of quantum mechanics. The result is a vision of space-time that is as radical and as beautiful as that of string theory, but which arises from a completely different set of principles. In LQG, space is not a smooth, continuous background. It is a discrete, granular structure, a quantum fabric woven from fundamental, indivisible atoms of space. These atoms are not in space, they are space. Each of these quantum atoms has a volume on the order of the Planck length cubed, the smallest possible volume that can exist. And these atoms are not just scattered randomly, they are connected to each other in a complex, evolving network, a spin network. The geometry of space, the very concepts of area and volume, are determined by the combinatorial properties of this network. And the evolution of this spin network in time creates a spin foam, a quantum, four-dimensional space-time. This is a profound and radical idea. It suggests that the smooth, continuous space-time of our macroscopic experience is an illusion, an emergent property of a much deeper, discrete, and quantum reality, in the same way that the smooth, continuous flow of water is an emergent property of the discrete, jiggling motion of a vast number of H2O molecules. This quantization of space-time has a powerful and immediate consequence. It eliminates the singularities of general relativity. In LQG, there can be no such thing as an infinitely dense point. The granular nature of space itself provides a fundamental minimum size, a quantum bounce that prevents the catastrophic collapse to a singularity. When this idea is applied to the Big Bang, the initial singularity is replaced by a big bounce. In this scenario, our expanding universe may have been preceded by a previous contracting universe, as this previous universe collapsed under its own gravity. It did not reach a singularity. Instead, when it reached the Planck density, the repulsive quantum gravitational effects of the space-time foam became dominant, causing the collapse to halt and bounce into the expanding phase of our own universe. The Big Bang was not a beginning, but a transition. Similarly, at the center of a black hole, the singularity is replaced by a Planck star, an incredibly dense but finite object where the collapsing matter is held up by the quantum pressure of space-time itself. This Planck star may eventually, after the black hole has evaporated through Hawking radiation, bounce and release the information that was trapped inside, providing a potential solution to the black hole information paradox. LQG is a beautiful and conceptually powerful theory, and it has had a number of significant successes, such as providing a first principles calculation of the entropy of a black hole. But it is also a theory that is still very much a work in progress. It has struggled to show how the smooth, classical spacetime of general relativity can emerge from its underlying discrete quantum structure. And it does not, as yet, provide a natural unification of gravity with the other forces and particles of the Standard Model. The debate between string theory and loop quantum gravity is one of the central intellectual dramas of modern theoretical physics. They are two, very different and seemingly incompatible, paths to the same ultimate goal. Whether one of them will prove to be correct, or whether the true theory of quantum gravity will be something else entirely, a synthesis of ideas from both remains to be seen. But the very existence of a theory like LQG is a powerful testament to the fact that our understanding of space and time is still in its infancy, and that the true nature of the cosmic fabric may be far stranger, more discrete, and more beautifully quantum than we ever imagined. The legacy of Stephen Hawking's work on black holes is a profound and beautiful illustration of the deep and fruitful interplay between general relativity, quantum mechanics, and thermodynamics. It is a story that begins with a simple observation about the area of a black hole's event horizon and ends with a deep and troubling paradox about the very nature of information. In the early 1970s, Hawking proved a powerful theorem in classical general relativity, the area theorem, which states that the surface area of a black hole's event horizon can never decrease over time. It can only stay the same, or increase, as the black hole swallows more matter. This had a striking and familiar ring to it. There is another quantity in physics that is famous for never decreasing entropy, the measure of a system's disorder, as described by the second law of thermodynamics. This led the Israeli-American physicist Jacob Bekenstein to make a bold and brilliant proposal that the area of a black hole's event horizon is, in fact, a measure of its entropy. This was a radical idea. In classical thermodynamics, entropy is related to temperature, and an object with entropy must have a temperature, and an object with a temperature must radiate energy. But in classical general relativity, black holes are perfectly black. Nothing can escape them. They should have a temperature of absolute zero. At first, Hawking himself was deeply skeptical of Bekenstein's idea. He set out to prove it wrong by applying the principles of quantum field theory to the curved spacetime around a black hole's event horizon. And what he found was one of the most stunning and unexpected discoveries in the history of physics. He found that Bekenstein was right. Black holes are not completely black. They do have a temperature, and they do radiate. due to the quantum fluctuations of the vacuum near the event horizon, a process that is now known as Hawking radiation. Black holes slowly, almost imperceptibly, emit a faint thermal radiation of particles. This discovery beautifully unified the three great pillars of modern physics. The formula for the temperature of a black hole contains Planck's constant, Newton's gravitational constant, and Boltzmann's constant. It is a single, elegant equation that connects all three domains of reality. And it confirmed Bekenstein's intuition: the entropy of a black hole is indeed proportional to the area of its event horizon. This led to the formulation of the generalized second law of thermodynamics, which states that the total entropy of the universe, the sum of the entropy of the ordinary matter and radiation outside the black hole, and the entropy of the black hole itself, can never decrease. If you throw a hot cup of tea into a black hole, the entropy of the outside world decreases, but the entropy of the black hole, as measured by its area, increases by an even greater amount, ensuring that the total entropy of the universe always goes up. The laws of black hole thermodynamics are a beautiful and profound extension of the laws of classical thermodynamics to the realm of gravity and quantum mechanics. But Hawking's discovery also created a deep and troubling puzzle: the black hole information paradox. Quantum mechanics is built on the principle of unitarity, the idea that information is never truly lost. The wave function of the universe contains all the information about its past, present, and future, and it evolves in a perfectly deterministic way. But black holes seem to violate this principle. If you throw an encyclopedia into a black hole, all the complex information contained in its pages seems to be lost forever behind the event horizon. And when the black hole eventually evaporates through Hawking radiation, the radiation it emits is purely thermal, random, and seems to contain no memory of the specific information that fell in. So, where did the information go? Is it truly destroyed, in violation of the most fundamental principle of quantum mechanics, or does it somehow escape, subtly encoded in the quantum correlations of the outgoing Hawking radiation? This paradox has been at the center of theoretical physics for decades, and it has led to some of our deepest insights into the nature of quantum gravity. Loop quantum gravity, with its discrete quantum geometry, offers a potential solution. In LQG, the singularity at the center of a black hole is replaced by a Planck star, and the information that falls into the black hole may be preserved in this quantum remnant, to be released at the very end of the black hole's evaporation. String theory, with its holographic principle, offers another. It suggests that the information is never truly lost inside the black hole, but is encoded on the two-dimensional surface of its event horizon, like a cosmic hologram, and is then slowly and subtly imprinted onto the outgoing Hawking radiation. The information paradox is a sign that we are at the very edge of our understanding, at the point where our two great theories of reality, general relativity and quantum mechanics, collide in a spectacular and beautiful contradiction. The resolution of this paradox will require a new, deeper, and more unified theory of nature, a theory of quantum gravity that can finally tell us the ultimate fate of the information that dares to venture beyond the point of no return. The fundamental nature of our universe, as revealed by our most successful physical theories, is that of a world built from quantum fields. This is the central insight of the standard model of particle physics and the broader framework of quantum field theory. The universe is not a collection of solid, inert, billiard ball-like particles. It is a vast, interconnected, and dynamic web of invisible, all-pervading fields. There is an electron field, a photon field, a Higgs field, and so on, one for each of the fundamental constituents of nature. The particles that we observe in our experiments are just the localized, quantized vibrations, the quanta of these underlying fields. An electron is a ripple in the electron field. A photon is a ripple in the electromagnetic field. And the forces between these particles are mediated by the exchange of other ripples, other quanta, the force-carrying bosons. This is a profound and radical shift in our worldview, a shift from a world of things to a world of processes, from a world of substance to a world of form. But this beautiful and powerful picture has a deep and unresolved tension at its heart, a tension that arises when we try to incorporate the force of gravity into this quantum field theoretic framework. In the Standard Model, the other three forces are described as quantum fields that exist on a fixed, pre-existing stage of space-time. But in Einstein's theory of general relativity, gravity is not a force that exists on the stage. It is the stage. Gravity is the dynamic, curving geometry of space-time itself. So, to build a quantum theory of gravity, we must quantize space-time. This is the central challenge, and it is a challenge that has led to two very different and seemingly incompatible approaches. The first approach, the one favored by most of the particle physics community, is to treat gravity like the other forces. In this view, there should be a graviton field, a quantum field of gravity that exists on a fixed background space-time, and there should be a corresponding quantum particle, the graviton, a massless spin-tube boson that mediates the gravitational force. When two massive objects attract each other, they are exchanging virtual gravitons. This is a natural and appealing picture, and it is the picture that underlies string theory, where the graviton emerges as one of the vibrational modes of the fundamental string. The problem with this approach is that when you try to apply the standard techniques of quantum field theory to the graviton field, the calculations are plagued by uncontrollable, non-renormalizable infinities. The theory breaks down at high energies. The second approach, the one taken by loop quantum gravity, is more radical. It takes Einstein's central insight that gravity is geometry seriously, and it attempts to quantize geometry itself. In this background-independent approach, there is no pre-existing stage of space-time. Space-time itself is an emergent quantum phenomenon, a dynamic network of interconnected atoms of space and time. In this picture, there is no need for a graviton particle that travels through space to mediate the force of gravity. Gravity is simply the large-scale, collective behavior of the quantum geometry of space-time itself. So, where does this leave the graviton? Is it a fundamental particle or a convenient fiction? The answer may be that it is both and neither. The wave-particle duality of quantum mechanics tells us that the distinction between a wave and a particle is not absolute. A gravitational wave, a ripple in the fabric of space-time, can also be thought of as a coherent stream of a vast number of gravitons, in the same way that a beam of light can be thought of as a stream of photons. The detection of gravitational waves in 2015 by the LIGO experiment was a stunning confirmation of one of the key predictions of general relativity. And while we cannot detect an individual graviton, it is reasonable to infer that these waves are, in fact, made of a vast number of these quantum particles of gravity. In the same way, the vibrational modes of a crystal lattice, which are waves, can also be described as quantum particles, called phonons. Phonons are not fundamental particles, but are quasi-particles, emergent, collective excitations of the underlying atomic lattice. Perhaps the graviton is like a phonon. It is not a fundamental particle that exists on a fixed background, but is an emergent, collective excitation of the underlying, discrete quantum geometry of space-time itself. This would be a beautiful synthesis of the two, seemingly opposing, views. Gravity is geometry, as Einstein taught us. But that geometry is, at its core, a quantum system, and its ripples, its vibrations, its quanta, are what we call gravitons. The search for a quantum theory of gravity is a search for the deep, underlying language that can speak of both the geometric elegance of Einstein's cosmos and the probabilistic quantum nature of the subatomic world. And in this new language, the old classical distinctions between space, time, matter, and force may all dissolve into a new, more profound, and more beautiful unified reality. The standard model of inflationary Big Bang cosmology, while stunningly successful, is a story that begins in the midst of the action. It describes the evolution of the universe from a hot, dense, and rapidly expanding initial state. But it is silent on the question of the ultimate origin. It is a story with a first chapter, but no preface. The initial singularity, the point of infinite density and temperature where the story begins, is not a physical reality, but a confession of ignorance, a point where our current laws of physics break down. To understand what might have come before the Big Bang, or what might have caused it, we must venture beyond the realm of classical general relativity and into the strange and speculative world of quantum cosmology. And it is here, in the application of quantum principles to the universe as a whole, that we find a number of fascinating and potentially revolutionary new ideas. The central challenge is to build a theory of quantum gravity, a theory that can describe the universe in its earliest, most extreme moments, when both quantum effects and strong gravity were important. Loop quantum gravity, with its vision of a discrete, granular space-time, offers one of the most well-developed approaches to this challenge. And when the principles of LQG are applied to the early universe, a remarkable and beautiful picture emerges. The Big Bang singularity is gone. It is replaced by a big bounce. In this scenario, our expanding universe was preceded by a previous contracting universe. As this parent universe collapsed under its own gravity, it did not fall into an infinitely dense singularity. Instead, when it reached the incredibly high but finite Planck density, the discrete quantum nature of space-time itself kicked in. The atoms of space resisted being squeezed any further, creating a powerful, repulsive quantum gravitational force that halted the collapse and caused the universe to bounce into the expanding phase of our own cosmic eon. The Big Bang was not a beginning from nothing, but a transition, a moment of cosmic rebirth. This is a profoundly elegant and satisfying idea. It eliminates the problematic singularity, and it opens up the possibility of a universe that is eternal and cyclical. The history of the cosmos is no longer a linear story with a mysterious singular beginning, but an endless rhythmic dance of expansion and contraction, of death and rebirth. The development of this loop quantum cosmology has been a long and painstaking process, a journey of refining the mathematical models and the computational simulations to get a physically sensible picture. Early versions of the theory had their own problems, but through years of dedicated work, a consistent and robust model has emerged. In this model, the effects of quantum geometry appear as a correction to the classical equations of Einstein's general relativity. This correction term becomes significant only at extremely high densities, close to the Planck scale. At lower densities, the quantum effects are negligible, and the theory smoothly reproduces the predictions of classical general relativity, a crucial requirement for any new theory. The LQC model of the Big Bounce is not just a beautiful qualitative idea. It makes specific, testable predictions. It predicts a slightly different pattern of fluctuations in the cosmic microwave background than the standard inflationary model, a difference that could, in principle, be detected by future high-precision CMB experiments. It also offers a natural mechanism for generating a period of inflation after the bounce, potentially solving the horizon and flatness problems without the need for a separate, ad hoc inflaton field. The journey to understand our ultimate origins is a journey to the very heart of the mystery of time, of space, and of existence itself. And while we are still far from a final, definitive answer, the vision of a bouncing, cyclical, and eternal universe offered by loop quantum cosmology is one of the most compelling and beautiful stories that modern science has to tell. It is a story that replaces a singular, inexplicable miracle with a natural, dynamic, and potentially endless cosmic process. A story that suggests that our universe is not a one-off event, but a single, precious breath in the infinite and eternal respiration of the cosmos. The formation of our own solar system, a seemingly local and familiar event, is a story whose roots stretch back to the very beginning of the universe and are governed by the same deep, quantum mechanical principles that shape the cosmos at its largest and smallest scales. The story begins, as all cosmic stories do, in the aftermath of the Big Bang. The initial, hot, dense soup of particles cooled and expanded, and the tiny quantum fluctuations of the early universe were stretched to astronomical scales, seeding the first, large-scale structures of the cosmic web. Within the dense filaments of this web, vast clouds of hydrogen and helium gas began to collapse under their own gravity, fragmenting into the first galaxies and the first generations of stars. It was in one such cloud, in a quiet, suburban spiral arm of the Milky Way galaxy, about 4.6 billion years ago, that our own solar system began to take shape. The process of star and planet formation is a delicate and complex dance between the inward pull of gravity and the outward push of pressure and radiation, a dance that is, at its core, a quantum mechanical one. As a dense clump within a molecular cloud begins to collapse, it forms a spinning, central protostar, surrounded by a flattened, rotating protoplanetary disk of gas and dust. It is from this disk that the planets are born, and the very process that powers the young sun at the center of this disk is a quantum mechanical miracle nuclear fusion. In the incredibly hot and dense core of the protostar, the conditions are not quite extreme enough for hydrogen nuclei to overcome their mutual electrostatic repulsion and fuse together, according to the laws of classical physics. It is only through the strange probabilistic magic of quantum tunneling that these nuclei can get close enough for the strong nuclear force to take over, igniting the stellar furnace and beginning the long, stable, hydrogen-burning phase of the star's life. Without quantum tunneling, our sun would never have ignited, and our solar system would be a cold, dark, and lifeless place within the protoplanetary disk. The process of planet formation is also governed by quantum principles. At the microscopic level, tiny submicron dust grains, coated with a mantle of water ice and other frozen volatiles, begin to stick together. The forces that govern this initial clumping, the van der Waals forces, the electrostatic interactions, are all fundamentally quantum electrodynamic in nature. As these dust grains grow into larger pebbles, and the pebbles into kilometer-sized planetesimals, the process becomes dominated by gravity. But the very existence of the solid matter from which these planetesimals are built is a quantum story. The heavy elements that make up the rocky terrestrial planets, like our Earth, the carbon, the oxygen, the silicon, the iron, were not created in the Big Bang. They were forged in the nuclear furnaces of previous generations of massive stars. These stars, at the end of their lives, exploded as supernovae, scattering these newly created elements across the galaxy, enriching the interstellar medium and providing the raw chemical materials for the next generation of stars and planets. The very process of nucleosynthesis, the creation of these heavy elements, is a quantum mechanical one, governed by the laws of the strong and weak nuclear forces. We are, in the most literal sense, the children of the stars, our bodies made of the recycled ash of long-dead suns. Even the final architecture of our solar system, the stable, ordered arrangement of the planets in their orbits, is a product of its quantum origins, the distribution of mass and energy in the primordial protoplanetary disk. A distribution that was itself a relic of the initial quantum fluctuations of the universe. Determined the locations where planets could form and the amount of material that was available for them to accrete. The stability of our solar system, the delicate gravitational dance that has allowed for the long, uninterrupted period of climatic stability that was necessary for the evolution of complex life on Earth, is a fortunate consequence of this initial quantum roll of the dice. The story of our solar system's birth is a beautiful and powerful illustration of the deep, seamless connection between the microscopic and the macroscopic, between the quantum and the cosmic. It is a story that shows us that our own familiar world is not a separate, classical reality, but is a direct and intricate expression of the same, deep, quantum mechanical laws that govern the entire, vast and mysterious universe. The classical picture of a black hole, as a simple, featureless object described only by its mass, charge, and spin, has been profoundly enriched and complicated by the insights of quantum mechanics. The discovery of Hawking radiation revealed that black holes are not the eternal, static prisons they were once thought to be, but are dynamic, thermodynamic objects that have a temperature, an entropy, and a finite lifespan. But the quantum world has more surprises in store. The familiar Schwarzschild black hole, which is non-rotating and uncharged, is the simplest possible solution to Einstein's equations. But in the real universe, most black holes are likely to be spinning, a consequence of the angular momentum of the star that collapsed to form them. A spinning, or Kerr. Black hole is a far more complex and bizarre object. Its rotation drags the very fabric of space-time around with it, a phenomenon known as frame dragging. Near the event horizon, this effect is so strong that it creates a region called the ergosphere, a place where nothing can stand still. Any object in the ergosphere is forced to co-rotate with the black hole. This frame dragging has profound quantum mechanical consequences, the Penrose process. A theoretical mechanism proposed by Roger Penrose suggests that it is possible to extract energy from a spinning black hole. A particle entering the ergosphere can split into two, with one particle falling into the black hole and the other escaping with more energy than the original particle had. The extra energy is effectively stolen from the black hole's rotational energy. Quantum mechanics adds a new twist to this. The constant creation of virtual particle pairs in the vacuum near the ergosphere can lead to a quantum version of the Penrose process, a phenomenon known as superradiance, which can amplify certain types of waves and extract energy from the black hole, causing it to spin down over time. Black holes can also have electric charge, creating a Reissner-Nordstrom black hole. The combination of gravity and electromagnetism around such an object creates a complex and fascinating environment. The presence of the electric field can affect the process of Hawking radiation, preferentially creating charged particle pairs from the vacuum. And in some extreme of theoretical cases, a charged and spinning Kerr-Newman black hole can have a naked singularity. A singularity that is not hidden behind an event horizon, a possibility that most physicists find deeply troubling, as it would represent a breakdown of causality, a place where the future is not determined by the past. The idea of extra dimensions, as predicted by string theory, adds another layer of exotic possibility. In a higher dimensional universe, black holes may not be spherical. They could be black strings, extending like a line in the extra dimensions, or black brains, two-dimensional surfaces. These higher dimensional black holes would have different thermodynamic properties and would evaporate through Hawking radiation in different ways. The search for these effects, either through gravitational wave observations of black hole mergers or through experiments at the Large Hadron Collider, is one of the most exciting frontiers in the search for extra dimensions. The study of black holes has also inspired the development of analog models in the laboratory. By using systems like flowing fluids, Bose-Einstein condensates, or even special optical materials, physicists can create dumb holes or optical black holes, systems that have an event horizon for sound waves or light waves. These analog models have allowed for the experimental observation of effects that are similar to Hawking radiation, providing a powerful, if indirect, confirmation of one of Hawking's most profound and counterintuitive predictions. The quantum world of black holes is a realm of incredible richness, complexity, and mystery. It is the ultimate laboratory for testing the interplay of our two most fundamental theories of nature, a place where gravity, quantum mechanics, thermodynamics, and information theory all come together in a beautiful and challenging synthesis. And it is a place that continues to yield deep and surprising insights into the fundamental nature of space, of time, and of reality itself. The black hole information paradox, the profound and troubling conflict between the predictions of general relativity and quantum mechanics, has been one of the central and most fruitful battlegrounds in theoretical physics for the last 50 years. The paradox, in its essence, is this: general relativity says that anything that falls into a black hole is lost forever, its information hidden behind the one-way membrane of the event horizon. Quantum mechanics, on the other hand, insists that information can never be truly destroyed, that the total amount of information in a closed system must be conserved. When a black hole evaporates through Hawking radiation, this conflict comes to a head. Does the information that fell into the black hole escape with the radiation, or is it destroyed forever? In violation of the most fundamental principle of quantum mechanics, the resolution of this paradox is thought to be a key stepping stone towards a full theory of quantum gravity. One of the most promising and powerful ideas to have emerged from this quest is the holographic principle, a concept first proposed by Gerard 't Hooft and later developed by Leonard Susskind. The principle is based on a surprising observation about the entropy of a black hole. The entropy of a normal thermodynamic system is proportional to its volume, but the entropy of a black hole, as shown by Bekenstein and Hawking, is proportional to the area of its event horizon. This suggests that all the information about the three-dimensional interior of the black hole is somehow encoded on its two-dimensional boundary. The event horizon, much like a three-dimensional image, can be encoded in a two-dimensional hologram. The holographic principle generalizes this idea, proposing that the entire universe may be a hologram. It suggests that all the information contained within a volume of space can be described by a theory that lives on the boundary of that space, a theory with one fewer spatial dimension. This is a staggering and deeply counterintuitive idea. It suggests that the three-dimensional world we experience may be an illusion, a projection of a more fundamental, two-dimensional reality that exists on some distant, cosmic screen. The most concrete and successful realization of this idea is the ADS-CFT correspondence, or gauge gravity duality, discovered by the physicist Juan Maldacena in 1997. This is a remarkable mathematical conjecture that proposes an exact equivalence, a duality, between a theory of quantum gravity in a specific, five-dimensional, negatively curved spacetime called anti-de Sitter space, and a more conventional, lower-dimensional quantum field theory that lives on the four-dimensional boundary of that space. The two theories look completely different, but they are, according to the duality, just two different mathematical descriptions of the same underlying physical reality. Anything that happens in the five-dimensional gravitational bulk has a corresponding description in the four-dimensional non-gravitational boundary theory, and vice versa. This correspondence provides a powerful new tool for studying some of the deepest problems in physics. It allows us to translate difficult, unsolved problems in quantum gravity into more tractable and well-understood problems in quantum field theory. And it offers a potential holographic solution to the black hole information paradox. In the Arishoasis CFT correspondence, the evaporation of a black hole in the five-dimensional bulk is equivalent to a normal, unitary, information-preserving quantum process in the four-dimensional boundary theory. Since the two theories are just different descriptions of the same reality, and since information is conserved in the boundary theory, it must also be conserved in the bulk. The information that falls into the black hole is not lost. It is holographically encoded on the boundary, and it escapes with the Hawking radiation in a way that preserves unitarity. The holographic principle and the ADSOI's CFT correspondence are some of the most profound and powerful ideas to have emerged from theoretical physics in the last few decades. They suggest a radical new picture of reality, a world where space, time, and gravity may not be fundamental, but are emergent, holographic properties of a deeper, underlying quantum informational reality. While the correspondence has only been proven for a specific and rather unrealistic type of spacetime, it is a powerful proof of principle. It shows that a consistent quantum mechanical and holographic theory of gravity is possible. And it provides us with a new and deeply beautiful lens through which to view the universe. A lens that suggests that the ultimate secrets of the cosmos may not be written in the language of matter and energy, but in the subtle, quantum, and holographic language of information itself. The journey to understand the ultimate nature of reality, to find a single, unified theory that can describe all the forces and particles of nature, has led us to some of the most abstract and beautiful ideas in the history of science. From the vibrating strings of string theory to the quantum foam of loop quantum gravity, we are pushing the boundaries of our mathematics and our imagination. And yet, this quest is also a deeply empirical one, a quest that is constantly being guided, constrained, and inspired by the data we gather from our observations of the universe. We are living in a golden age of cosmology, a time of unprecedented observational power, a time when a new generation of telescopes and experiments is poised to answer some of the longest-standing questions in science, and to open up new, unforeseen windows onto the cosmos. The James Webb Space Telescope, with its giant golden eye, is already revolutionizing our view of the early universe, peering back in time to see the first galaxies and stars lighting up the cosmic darkness. The Vera C. Rubin Observatory, with its vast digital camera, will soon begin a decade-long survey of the southern sky, creating the deepest and most detailed movie of the universe ever made. A movie that will allow us to trace the history of cosmic expansion, to map the invisible scaffolding of dark matter, and to catch the fleeting glimmers of cosmic explosions. The Square Kilometer Array, a continent-spanning radio telescope, will map the three-dimensional structure of the cosmos by observing the faint, ancient radio waves from neutral hydrogen, giving us an unprecedented view of the cosmic dawn and the epoch of ionization. And the Laser Interferometer Space Antenna will take gravitational wave astronomy into space, allowing us to hear the gentle, low-frequency ripples in space-time from the mergers of supermassive black holes and, perhaps, from the very first, violent moments of the Big Bang itself. These are just a few of the incredible instruments that will shape the future of cosmology. They will provide us with a wealth of new data that will test our current theories to their breaking point, data that will challenge our assumptions, and data that will undoubtedly reveal new and unexpected puzzles. What is the nature of dark matter? What is the true identity of dark energy? Did cosmic inflation happen? And if so, how is our universe the only one? Or are we part of a vast cosmic multiverse? Is there life beyond Earth? These are the great open questions of our time, and we are, for the first time in human history, on the verge of being able to answer some of them with real, hard, scientific data. But the quest to understand the origin of the universe is more than just a scientific one. It is a deeply human one. It is a quest that is driven by our innate and perhaps unique capacity for wonder, for curiosity, for the desire to know our place in the grand cosmic scheme of things. It is a quest that connects us to our most ancient ancestors, who looked up at the same star-filled sky and asked the same fundamental questions. And it is a quest that has the power to unite us, to remind us of our shared cosmic heritage and of our common fragile home on this small blue planet. As we stand on the threshold of a new era of discovery, we are filled with a sense of both profound humility and exhilarating excitement. We are humbled by the vastness of the cosmos and the depth of our own ignorance, but we are also excited by the incredible power of the human mind to comprehend, to explore, and to understand. The journey is far from over. The greatest adventures, the most profound revelations may still lie ahead, waiting for us in the deep, silent, and beautiful darkness that lies just beyond the horizon of our current understanding. And as you close your eyes and let the universe of your own mind unfold in the quiet theater of your dreams, you can feel a sense of participation in this grand human adventure. The consciousness that is about to journey into the mysterious inner cosmos of sleep is the same consciousness that is, at this very moment, reaching out to the stars, listening for the echoes of creation, and striving to read the silent, beautiful, and endlessly fascinating story of the universe. Good night, and may your dreams be as vast and as wonderful as the cosmos itself.